Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. In the silent darkness of space, a star dies. For a brief moment, it outshines everything around it, a beacon of unimaginable brilliance piercing the void. What was once a steady pinprick of light in the night sky suddenly blossoms into a furious brightness, only to fade away and vanish. This is the paradox of a supernova, the explosive death of a star that looks to us like the appearance of a new one. In that instant of violent death, something new is born in its wake. We watch from our tiny world with both wonder and humility. Across the gulf of light, years, a distant sun has reached the end of its life and unleashed an energy beyond comprehension. It is an end in the most dramatic fashion possible, a final act that illuminates the cosmos. Yet it is also a beginning. The star's death throes scatter the heavy elements forged in its heart out into space, seeding the darkness with the ingredients for new stars, new planets, perhaps new life. In dying, the star becomes a cosmic phoenix. Its ashes enrich the galaxy and fertilize the universe. In a supernova's fleeting flash, we witness a cycle as old as the cosmos itself, creation and destruction entwined. The universe began with light, and in each stellar death, there is a small echo of that beginning, a burst of radiance, a flood of particles and atoms hurled outward to partake in future creations. Every one of us carries the story of these explosions in our bodies, the iron in our blood, the calcium in our bones, the oxygen we breathe. Those atoms were forged in stellar furnaces and scattered by stellar explosions long before the Earth coalesced. We are, quite literally, made of stardust, born from the remnants of ancient supernovae. So when we look up at the night sky, we are not just seeing stars, we are seeing memories. Each point of light is a story that may one day end in a supernova, as countless stars have before. Some of those stories ended eons ago, their light only now reaching us, bearing news of cosmic endings that were also cosmic beginnings. In the darkness between the stars, there are ghosts, expanding clouds of gas and dust that were once suns. And there are futures, nascent stars, forming in nebulae enriched by those past explosions. This is the tale of supernovas, at once an elegy and a celebration. It is the tale of how stars live, die, and transform the universe. It is a story written across millions of years, but observable in a single human lifetime as a sudden blaze in the sky. Together, we will journey through this story. We will witness the birth of a star and follow its life to the cataclysmic moment when the core collapses. We will explore the different kinds of supernovae that nature has devised and see how these brilliant events have touched human lives and imaginations throughout history. We will visit the most famous stellar explosions known to science and what they left behind. Beautiful nebulae, spinning neutron stars, perhaps even black holes that swallow all light. As we voyage through time and space in our collective imagination, we will see how supernovas are not random acts of destruction, but essential threads in the fabric of the cosmos. They are beacons, guiding our understanding of distant galaxies, engines driving the evolution of those galaxies, and perhaps harbingers of danger in our own cosmic neighborhood. They are the universe's great alchemists, forging heavy elements and sewing them far and wide. And in their afterglow, we find insight into the deepest mysteries of existence, including our own origins. Let us begin at the beginning of a star's life. Because to understand the death of a star, we must first understand how it lives. In the cosmic theater, every death scene is set by the long life that came before it. And so we step back to watch a star being born, knowing that in its birth lie the seeds of its demise and the promise of everything that will follow. The life cycle of stars. Before a star can die, it must live. Our journey begins in a vast, cold cloud of gas and dust, drifting in the galactic night, a stellar nursery waiting for a spark. In these dark, silent nebulas, gravity gradually draws denser clumps together. We imagine ourselves floating there as one particular clump, maybe a little larger than the rest, starts to collapse under its own weight. As it compresses, it heats up and begins to glow with a faint reddish light. We have witnessed the birth of a protostar, the first flicker of a new sun. In time, the growing protostar's core becomes hot and pressurized enough to ignite nuclear fusion. When its central temperature climbs to tens of millions of degrees, hydrogen atoms begin fusing into helium. With that first flash of fusion fire, a true star is born. It stabilizes, entering the long, steady middle of its life known as the main sequence. For millions to billions of years, this young star will shine, a blazing sphere of plasma held up against gravity by the continuous energy of fusion. In this stage, a delicate balance is struck. The inward pull of gravity and the outward push of radiant heat are in equilibrium. The star has found its rhythm, a stable heartbeat in the darkness. We look around and see countless stars on the main sequence, each with its own life clock ticking at a different rate. The massive ones, dozens of times heavier than our sun, burn their fuel extravagantly and live fast, shining hot and blue, white. They may spend only a few million years in this stable phase. Smaller stars, like our sun, burn more moderately and can shine for tens of billions of years. And the tiniest red dwarfs, barely heavy enough to ignite fusion, sip their fuel so slowly that they could outlive galaxies, trillions of years into the future. A star's mass is its fate. It determines how luminous the star is and how long it will live. As the eons pass, even the most enduring stars exhaust their primary fuel. In the core of a middle-aged star, like our sun, the hydrogen that once fused so plentifully is gradually converted to helium. When the core fuel runs low, the star begins to change. We watch as our once stable star starts to swell and redden, transforming into a red giant. Its outer layers puff outward, cooling and glowing a deep sunset hue. In its core, new fusion reactions ignite as helium fuses into carbon and oxygen. For a while, the star finds a new balance, but it is precarious, a sign of old age. For a star of modest size, this red giant phase is the prelude to a quiet death. When the helium is finally spent, such a star cannot muster the temperatures needed to fuse heavier elements. The core, now a hot ball of carbon and oxygen ash, begins to contract, while the outer layers become unstable. Gently, at least by cosmic standards, the star sheds its outer envelope into space, creating a glowing shell of gas called a planetary nebula. What remains at the center is the star's tiny, exposed heart, a white dwarf, no bigger than Earth, made of degenerate matter and slowly cooling over eternity. This is one possible end of the stellar life cycle, a hushed fading rather than a cataclysm. The once grand star becomes a faint ember, and the beautiful planetary nebula disperses into the interstellar medium over tens of thousands of years. But our focus is on a far more dramatic finale, one reserved for the giants among stars. Let us rewind a bit and follow the life of a truly massive star, say 10 or 20 times the mass of the Sun. These behemoths blaze blue, white, and live brief, brilliant lives. They race through their fuel, shining millions of times brighter than the Sun, and expending their core hydrogen in mere millions of years. When hydrogen runs out, the transition is anything but gentle. The core contracts and heats rapidly, and the star balloons into a red supergiant, enormous enough to engulf entire planetary systems. Betelgeuse, the red shoulder of Orion, is one such star nearing this final act, bloated, unstable, and nearing the end of its supplies. Inside such a red supergiant, the core temperatures soar high enough to fuse helium into carbon and oxygen, and then, with frightening speed, to fuse those elements into heavier ones. The star's life accelerates toward its conclusion. In successive stages, carbon burns to neon and magnesium. Neon burns to oxygen, oxygen to silicon, and silicon to iron. We imagine peering into the heart of this titanic star in its last million years and seeing something like the layers of an onion, concentric shells of burning elements, hydrogen in the outer layers, then helium, carbon, oxygen, and so on, all feeding an increasingly ferocious furnace at the core. At last, the star builds an iron core deep in its center. Iron is a fatal milestone for a massive star, for when nuclei fuse into iron, no energy is released. The process that sustained the star's outward pressure grinds to a halt, as if a beating heart has suddenly stopped. The core can no longer support the crushing weight of the star's immense outer layers. For a brief moment, a tense silence falls inside the star, the calm before an unimaginable storm. This is the end of the star's life as a normal star. In the iron core, which may be about the size of Earth, but with over 1 billion times Earth's mass, no more thermonuclear miracles remain to stave off gravity. The star has reached the brink of catastrophe. All the glorious millions of years of shining have led to this precipice. The outward light falters, the balance is undone, and gravity prepares to exact its final victory. In that final moment, the stage is set for a collapse and an explosion, the supernova we have been waiting for. The life cycle of the star, from birth in a nebula to maturity in the main sequence to bloated old age, has brought it inexorably to an existential crisis. What happens next will be the subject of the following chapter in our story. A chapter written in fire and fury as the star's core collapses and a supernova is born. The final act, core collapse. The end comes swiftly and without mercy. In the heart of our massive star, the iron core has grown to a critical mass, roughly 1.5 times the mass of our Sun, compressed into a sphere barely 50 miles across. At this extreme, the familiar laws of matter are on the verge of breaking down. Gravity, long held at bay by the energy from fusion, finally has the upper hand. And then, in a fraction of a second, the core buckles. We find ourselves in the core at the moment of collapse. Temperatures have soared to over 10 billion degrees and rising. The iron nuclei, pressed unbearably tight, begin to disintegrate into smaller particles. Electrons are driven into protons, turning them into neutrons and releasing floods of ghost, like particles called neutrinos. The core's atoms, once the powerhouse of the star, are now crushed into an ultra-dense ball of neutrons. In the span of a heartbeat, the core implodes, matter-free, falling inward at speeds approaching a significant fraction of light. The densities reach astronomical levels, higher than those inside an atomic nucleus. For an instant, the core is like a giant atomic nucleus itself, a sphere of neutrons about the size of a city. Suddenly, this collapse slams to a halt. The neutron core, essentially incompressible, resists further squeezing. It's as if the star has hit a concrete floor at nearly 1/4 the speed of light. The infalling material recoils. In that violent rebound, a powerful shockwave is born at the core and begins plowing outward through the star. But the shock alone is not yet the famous supernova explosion. It threatens to stall as it loses energy, tearing apart iron nuclei in its path. For a brief moment, it seems the star might simply collapse and swallow itself quietly. Then something extraordinary intervenes. The flood of neutrinos. Remember those neutrinos produced as electrons and protons were crushed together? In the turmoil of the collapsing core, billions upon billions of neutrinos are streaming out. Normally, neutrinos hardly ever interact with matter. They can zip through an entire star as if it were empty space. But here, in the densest environment the universe can offer outside of a black hole, even neutrinos begin to collide with matter. They deposit a stupendous amount of energy into the infalling layers just behind the shock front. This energy is the spark that revives the dying shockwave. With neutrino power added to the rebound, the shock roars back to life, surging outward with renewed fury. Now the star truly explodes. Within less than a second, the core collapse has transformed into an outgoing detonation. The shockwave tears through the star's layers from inside out. The overlying material, hydrogen, helium, carbon, all the way to the surface, is blasted into space at incredible speeds. The pressures and temperatures are so immense that new nuclear reactions ignite in the chaos, forging elements heavier than iron in fleeting moments of neutron bombardment. Gold, uranium, and dozens of other heavy elements are synthesized in these last violent seconds, like the final flourish of a master craftsman finishing a grand work. From outside, we would see nothing of this cataclysmic ballet until the shock breaks the star's surface. One moment, the star was a red supergiant, perhaps shining a bit erratically. The next moment, boom. The surface of the star is abruptly ejected, and a brilliant flash of light known as the shock breakout occurs. The star's outer layers, now unleashed, race outward as an expanding fireball, glowing a hot blue, white from the immense heat of the explosion. Within hours, the brightness swells dramatically. Within days, the exploded star becomes one of the brightest objects in its galaxy. A supernova has appeared where a familiar star used to be. At the core of this expanding fury lies the crushed remnant of the star, the ball of neutrons that survived the collapse. It is extremely small and dense. If its mass is below a certain threshold, it will settle as a neutron star, a city-sized stellar corpse. If it's more massive, nothing can halt its collapse, and it continues shrinking to become a black hole, an abyss from which no light escapes. But in either case, that core is no longer producing light. All the radiance of the supernova comes from the explosion's aftermath, from radioactive isotopes created in the blast decaying and heating the debris, and from the shock heating the star's outer layers as they expand. The dying star's final scream echoes across the electromagnetic spectrum. First comes a burst of neutrinos, an invisible herald racing ahead of the light. Then, the light arrives, rapidly growing to a peak brightness that can rival an entire galaxy's output of stars. For weeks, too, months, the debris of the star glows intensely, powered by the decay of unstable isotopes forged in the fireball. We imagine watching from a safe distance as the shattered star's remains expand in a great spherical shell, cooling and dimming over time. Where once there was a mighty star, now there is a cloud of glowing ash, the embryonic form of a supernova remnant, and, hidden at the center, a compact new child of the cosmos born from the core's collapse. This is a core collapse supernova, the fate of massive stars. It is nature's grandest light show, a release of energy so colossal that for a short time, a single star's death outshines all the billions of stars in its galaxy. But not all supernovae follow this script. There is another type of stellar death, one that begins not with a massive living star, but with the quiet ember of a star that died long ago. Before exploring the remnants and outcomes of core collapse explosions further, we will take a detour to understand the other path to a supernova, the path of the white dwarf and the thermonuclear runaway. Two paths to destruction, Type 1 versus Type 2. Not all stars that go supernova do so in the same way. As astronomers studied the light from these stellar explosions, they found telltale differences. Some supernovae show signatures of hydrogen in their exploded debris. Others have no hydrogen lines at all. This was the first clue that there are two distinct paths to stellar oblivion. In the astronomical naming convention, those with hydrogen are called Type 2 supernovae, and those without are Type 1. We now understand that behind these spectral differences lie very different stories. The Type 2 supernova is the scenario we have just witnessed, the core collapse of a massive star that still had its hydrogen envelope at the time of explosion. The ejected material in a Type 2 supernova's spectrum reveals abundant hydrogen because the star was a red supergiant until the moment it died. These are the deaths of solitary massive stars, tearing themselves apart from the inside out. But what of the type 1, the ones that mysteriously lack hydrogen? It turns out some stars die by borrowing a kind of second life, and then blowing themselves to pieces in a thermonuclear fury. Imagine a star, much like our Sun. After living out its life and quietly shedding its outer layers, it ends as a white dwarf, a small, dense stellar corpse composed mostly of carbon and oxygen, with no ongoing fusion. Normally, a white dwarf simply cools over the eons, but if this white dwarf has a close companion star, fate may have a more explosive plan. Picture a binary star system where one star is a white dwarf and the other is a living star. The white dwarf, though dead in the sense of fusion, still exerts strong gravity. It begins siphoning gas from its companion, pulling hydrogen and helium off the neighboring star's outer layers. The stolen gas accumulates on the white dwarf's surface, compressing and heating. For a while, this theft goes unnoticed on a cosmic scale. The white dwarf grows more massive, creeping toward a critical limit, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. This is the maximum mass that a white dwarf, supported only by the quantum pressure of electrons, can hold without collapsing. When the white dwarf approaches this threshold, something incredible happens. The pressure and temperature at its center become high enough to ignite carbon fusion in a runaway manner. Unlike a normal star, the white dwarf has no way to regulate this burning. It is essentially a giant bomb waiting for a spark. The carbon fusion spreads rapidly in a wave through the dwarf's interior, unleashing a titanic thermonuclear explosion. In a fraction of a second, the entire white dwarf is obliterated in one of the most brilliant fireworks the universe has to offer, a Type Ia supernova. This Type Ia supernova is fundamentally different from the core, collapse Type 2. It is not a star's core imploding under gravity. It is a prompt detonation, a nuclear bomb on a stellar scale. The white dwarf is entirely destroyed. No neutron star or black hole is left behind, only an expanding cloud of debris. Because the explosion comes from the sudden fusion of about a sun's mass of carbon and oxygen, it tends to produce a very consistent brightness each time. In fact, Type Ia supernovae act as standard candles for astronomers. Since they all reach roughly the same peak luminosity, we can gauge their distances by how bright they appear. We'll revisit this idea later when we see how such supernovae helped map the universe. For now, consider what the lack of hydrogen in the Type 1 spectrum means. A white dwarf has no hydrogen envelope. It lost all that long ago when its progenitor star shed its outer layers. So when it explodes, the debris shows no hydrogen lines. That's how we know a supernova was likely a Type Ia. Its light is missing hydrogen and often shows a distinctive signature of iron and nickel from the burned outcore of the white dwarf. There are also other subclasses of Type 1. For instance, Type Ib and Type Ic supernovae are actually massive star explosions like Type 2, but ones that shed their outer hydrogen before exploding. These usually happen in massive stars that blew off their envelopes via strong winds or interactions in a binary system, leaving a bare core to collapse. Thus, they are core collapse supernovae like Type 2, only stripped of their outer layers, so they masquerade as Type 1 by lacking hydrogen in their spectra. It can sound alphabet, soup confusing, but the essence is this. One path to supernova is a single, massive star collapsing under gravity. The other path is a smaller star, a white dwarf, blowing itself apart in a nuclear runaway. Both paths produce immense explosions, but their causes and outcomes differ. In one, a stellar core implodes and might leave a dense remnant. In the other, a stellar remnant detonates and leaves nothing substantial behind at its center. Understanding these two fundamental types gives us insight into the variety of cosmic fireworks we observe. Some supernovae announce the dramatic death of a lone giant. Others signal the demise of a long-dead star, reignited by a companion. Together, Type 1 and Type 2 supernovae account for nearly all the stellar explosions we see lighting up distant galaxies. With this framework in mind, we can better appreciate the events and remnants we are about to explore. Now let us step out of the theoretical realm and into human history. Long before we unraveled the astrophysical mechanisms, people witnessed supernovae in the sky without knowing what they were. They saw brilliant new stars appear where none had been before, and grappled with their own interpretations. Our cosmic story now crosses paths with the human story as we look at supernovas through the eyes of those who saw them from Earth centuries ago. Supernovas in human history. Long before modern science unraveled the physics of supernovae, humans were witnessing these celestial events with naked eyes and recording their wonder and fear. To ancient sky watchers, the sudden appearance of a brilliant new star in the firmament was an astounding, often ominous event. The regular stars and planets followed known patterns, but a new star, a nova or guest star as some called it, defied the idea of an unchanging heaven. It was as if the cosmos itself had spoken in a burst of light. One of the earliest recorded supernovae occurred in 185 AD. Chinese astronomers noted a strange guest star in the southern sky. It lingered for about 8 months before fading away, enough time for ancient observers to take careful notice. They dutifully recorded its position and its disappearance in official court chronicles. We now know that this was indeed a supernova, and modern astronomers have rediscovered the faint traces of its remnant about 8,000 light years from Earth. That ancient record, largely qualitative and couched in the language of omens, aligns with the physical evidence we see today of a Type Ia supernova explosion that occurred nearly 2 millennia ago. In late April of the year 1006 AD, a staggeringly bright guest star exploded into Earth's skies in the constellation Lupus. It ultimately reached an estimated visual magnitude of around 7.5, so bright that it was visible during the day. Observers across Eurasia marveled at it. Historical records say it cast shadows at night and was even visible during the day. The Egyptian astronomer Ali ibn Ridwan wrote that it was a large star which appeared in the south, having an enormous luster, far outshining Venus. We believe this was the brightest supernova ever observed by humanity in recorded history, what we now call SN 1006. People all over the world took note, and in some places it stirred fear or was interpreted as a portent. In North America, a possible record exists in an ancestral Puebloan pictograph, a depiction of a star next to a crescent moon on a rock wall in Chaco Canyon, which some have interpreted as a representation of this guest star. Though intriguing, such interpretations remain debated. Just a few decades after that, on July 4th, 1054 AD, all of Earth was treated to celestial fireworks as another new star appeared, this time in the constellation Taurus, the Bull. Chinese court astronomers recorded that it was initially brighter than the moon and lingered in the sky for nearly 2 years before slowly fading from view. Unbeknownst to those observers, they were watching the birth of what we today call the Crab Nebula, the expanding remains of that exploded star. SN 1054 was likely a massive star's death. The memory of this event may also have been preserved outside East Asia. Medieval Japanese and Arabic records also mention a brilliant guest star around that time. And as mentioned, some interpret the rock art in the American Southwest as depicting the event. For medieval Europe, knowledge of these events was sparse. Europe in 1006 and 1054 was in the middle of the Dark Ages and early medieval period, and scholarly astronomy was less developed than in the Islamic world or China. Moreover, Aristotelian doctrine held sway. The heavens beyond the moon were thought to be immutable and unchanging. A bright new star did not fit that worldview and might even have been ignored or explained away by those who adhered to the idea of perfect, unchanging skies. Still, by the Renaissance a few centuries later, careful observers were starting to challenge that ancient dogma. In November 1572, sky watchers in Europe, including a young Danish astronomer named Tycho Brahe, were astonished by a brilliant star in the constellation Cassiopeia, where no star had been seen before. Tycho diligently observed this nova stella every night, measuring its position relative to the fixed stars. He found it showed no parallax, meaning it was far beyond the moon, out among the stars, which directly contradicted Aristotle's notion of an unchanging celestial realm. Tycho's supernova shone as bright as Venus for weeks. We now suspect SN 1572 was a Type Ia thermonuclear supernova, the kind involving a white dwarf. Modern studies of the remnant show no neutron star at the center, consistent with a Type Ia where the star was obliterated. For Tycho and his contemporaries, the event was pivotal. His observations, published in a work titled De Nova Stello, were a key piece of evidence that the heavens do change, helping pave the way for the new astronomy of Copernicus, Galileo, and Kepler. To the public and religious authorities, the new star was often seen as an omen. To Tycho, it was a scientific revelation. Only 32 years later, in October 1604, another brilliant star burst forth, this time in the constellation Ophiuchus. The famous astronomer Johannes Kepler observed it closely and wrote a book about it. SN 1604, or Kepler's supernova, became brighter than all stars and planets in the sky at its peak. Like Tycho's, it had no measurable parallax, further driving the nail into the coffin of the Aristotelian crystalline spheres theory. It was the last supernova observed in our Milky Way with the naked eye. Modern astronomers have studied Kepler's supernova remnant and, based on its characteristics, believe it too was likely a Type Ia event. Thus, the two great Renaissance supernovae were both thermonuclear explosions of white dwarfs, yet their appearance at critical moments in history had enormous impact on human thought, marking the end of an era when the cosmos was thought to be static and perfect. Throughout human history, only a handful of these new stars have been recorded, but each left an imprint on culture and science. From Chinese astrologers linking them to dynastic fortunes, to European scholars using them to question classical doctrines, supernovae have occasionally influenced the course of human thought. Most of the time, the stars live and die unseen. But when one does announce itself to us, it rarely goes unnoticed. These events also gradually built a bridge between myth and science. Each recorded observation, from 185 AD to 1572 to 1604, added a piece to the puzzle that modern astrophysicists would later assemble with telescopes and physics. Today, we can return to those historical supernovae with our scientific tools. The Crab Nebula still glows in our telescopes, and at its center, a pulsar, a rapidly spinning neutron star, blinks 30 times a second, the collapsed core left from that explosion. The remnants of Tycho's 1572 and Kepler's 1604 supernovae have been detected as expanding shockwaves in space, and careful measurements of their light, echoes, and debris composition have helped identify their type. In this way, the observations of long-ago sky watchers connect directly to the science we conduct now. The people of the past saw supernovas without understanding their true nature, but they carefully noted their appearance and timing. We, following in their footsteps, can point our instruments to those same locations centuries later to learn the why and how. It is a beautiful continuity of curiosity. Now, with the historical context in mind, let's focus on a few of those famous supernovae that have become legends in both astronomy and culture. The ones whose names have been mentioned, the mysterious guest star of 1054 that created the Crab Nebula, the brilliant new stars observed by Tycho and Kepler that altered the course of astronomy, and a much more recent stellar explosion that heralded the dawn of a new era in space observation. These are supernovas that stand out like beacons in human history's record of the sky. Witnessing great explosions, famous supernovas. Across the ages, certain supernova events stand out as especially notable, either for their brilliance, for the insights they gave us, or for the lore that surrounds them. Let us revisit a selection of these cosmic spectacles in more detail, to feel what it might have been like to witness them and to understand what they have taught us. SN 1054, the Crab Nebula's birth. It is summer in the year 1054. On a July night, people around the world gaze upward to find a startling new light in the heavens, near the starry outline of Taurus the Bull. Chinese astronomers in the Song dynasty record that it is as bright as Jupiter, eventually even brighter, visible in the daytime for weeks. They call it a guest star, and note its gradual fading over nearly 2 years. What those observers see is the death of a massive star, roughly 6,500 light years away. Today, when we point a telescope at that same spot, we see the Crab Nebula, a sprawling tapestry of filamentary gas and dust expanding in space. At its center, a tiny pulsar flashes 30 times a second like a cosmic lighthouse. This pulsar is the collapsed core of the star that exploded. The Crab Nebula, with its eerie tendrils of glowing gas, is essentially frozen fireworks from 1054, still expanding at thousands of kilometers per second. Studying it across different wavelengths has given astronomers invaluable insight into how supernova debris evolves and how neutron stars behave. One can imagine the awe of ancient sky, watchers seeing the initial explosion, not knowing that before them was the creation of a beautiful nebula that later astronomers would come to understand and marvel over. The Crab Nebula stands as a bridge between human history and astrophysics, a guest star turned enduring monument in the sky. Tycho's star of 1572. Fast forward to November 1572, Denmark. Tycho Brahe, returning from his evening walk, looks up and is astonished to see a brilliant star in the otherwise familiar pattern of Cassiopeia. A star that simply was not there the night before now shines proudly. Tycho quickly organizes systematic observations, measuring the star's position relative to the moon and known stars night after night. He finds, to his wonder and intellectual delight, that the new star exhibits no parallax, no shift against the distant star background from Earth's orbit. It must lie among the fixed stars, far beyond the moon, proving the heavens are not immutable. Tycho writes about this discovery in detail. The star shines with the brightness of Venus, then slowly fades over about 16 months. We now know SN 1572 was a Type Ia supernova, a thermonuclear explosion of a white dwarf star in a binary system. Its remnant, seen with modern telescopes, is an expanding cloud of gas with no pulsar or neutron star inside. Tycho's careful work on this supernova provided crucial evidence that the Aristotelian cosmos was flawed. It marked a paradigm shift. The universe beyond Earth was dynamic and changing. Culturally, Tycho's new star challenged theologians and philosophers. Scientifically, it propelled the likes of Kepler and Galileo to further question cosmic dogma. It is poignant that a dying star, which had likely been dead for thousands of years before its light reached Earth, helped spark the birth of modern astronomy. Kepler's supernova of 1604. Just 32 years after Tycho's event, the cosmos provided another spectacular display. In October 1604, in the constellation Ophiuchus, a new star blazed forth. It reached magnitude 2.5, outshining every star and planet in the night sky. The great mathematician and astronomer Johannes Kepler observed it extensively. People across Europe saw it. Kepler, much like Tycho, found that it showed no parallax. By this time, the Copernican view of the solar system was gaining traction, and Galileo would soon turn a telescope to the heavens. Kepler's supernova, though a brilliant apparition, was the last such to be observed in our Milky Way to date. Modern analysis of its remnant, using space telescopes, indicates it was likely a type Ia as well. Kepler compiled observations of the 1604 supernova, noting its color changes and steady decline in brightness over a year and a half. Kepler's work, published in De Stella Nova, along with Tycho's earlier nova, cemented the idea that the heavens evolve. Philosophically, it shook the last resistance to the notion that change and decay occur in the celestial realm just as on Earth. After Kepler's star, no new stars were seen in our galaxy, so these two Renaissance supernovae stand out as heralds of a new worldview. They bookend the 16th century's scientific revolution, and each bears the name of the astronomer who studied it because their observations were so influential. Supernova 1987A, a modern spectacle. For more than 300 years after Kepler's 1604 event, no supernova bright enough to see with the naked eye was observed, though many undoubtedly occurred hidden behind interstellar dust or on the far side of the galaxy. Then, on February 24, 1987, something historic occurred. A brilliant new star was spotted in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, visible to the naked eye in the southern hemisphere. This was the nearest supernova since Kepler's about 168,000 light-years away. Supernova 1987A was extraordinary, not just for being visible to modern humans, but for being studied with modern scientific tools. Prior to the visible light, detectors deep underground in Japan, the US, and the Soviet Union picked up a flurry of neutrinos, 24 neutrinos in total, arriving within a 13th of a second window, just hours before the supernova was seen. These ghostly particles were emitted from the collapsing core of the star and provided direct confirmation of the core collapse mechanism we described. It was the first time humanity caught neutrinos from beyond the solar system, and they came from a dying star's core. When the light arrived, telescopes around the world and above it turned to watch SN 1987A. They saw the rise and fall of its light, measured the nuclear isotopes powering its glow, and observed its debris expanding. SN 1987A turned out to be a bit of a surprise to theorists. The star that exploded was not a red supergiant, but a blue supergiant, a hotter, more compact star. It had likely been a red supergiant earlier, but perhaps merged with a companion or shed mass in a complex way that left it blue at the time of collapse. The star left behind a striking arrangement of glowing rings, material it had ejected in earlier epochs, which the supernova's blast wave has since been colliding with, producing a fireworks show of its own as the rings brighten in response. We are still observing 1987A decades later. It's a living laboratory for supernova physics. So far, no neutron star has been definitively seen inside, leaving a tiny bit of mystery. But we detected the cobalt and titanium produced in the explosion, confirming models of how elements are forged. We witnessed the light from the blast echo off interstellar dust, giving us different perspectives of the event. In short, 1987A was like an astrophysical Rosetta Stone, offering answers to long-standing questions and posing new ones. For people around the world in 1987, especially those in places like Australia or Chile, who could see the Large Magellanic Cloud in their night sky, the appearance of a new star was thrilling. Unlike in 1572, it didn't spark fear or philosophical crisis. Instead, it sparked celebration among astronomers and curiosity among the public. At observatories, champagne bottles were uncorked when the first neutrinos were confirmed and the optical counterpart was found. Humanity had waited centuries to see such an event up close, and now we finally had front row seats. SN 1987A inaugurated the era of multi-messenger astronomy, using not just light, but particles like neutrinos to study cosmic events. And it came just as computing and telescope technology allowed us to capture it in unprecedented detail. From the ancient guest star of 1054, recorded by Chinese astrologers, to the modern supernova of 1987, observed with neutrino detectors and space telescopes, our understanding has grown immensely. Each famous supernova has left an enduring legacy. The Crab Nebula's pulsar confirmed the existence of neutron stars. Tycho's and Kepler's observations helped dismantle the old cosmic order. SN 1987A gave direct confirmation of theory and a wealth of data on how supernovae work. They are shining milestones on our journey to comprehend the universe. Having witnessed what happens when stars explode, we turn now to one of the most profound consequences of these events: the creation of the very stuff that makes up planets and people. In the violent cauldrons of supernovae, elements are forged that otherwise would not exist. This is the story of nucleosynthesis, the cosmic alchemy carried out in stellar life and death. Stardust and elements, nucleosynthesis in supernovae. Every atom in our bodies has a story that stretches back to the stars. The golden ring on a finger, the calcium in our bones, the iron in our blood, all were forged in cosmic furnaces and explosive crucibles. Supernovae are not merely spectacular light shows, they are also the universe's great alchemists. To understand how, we must look at what happens deep inside stars and during those final explosive moments of their deaths. Throughout a massive star's life, its core is a fusion factory, sequentially forging heavier elements out of lighter ones. Hydrogen fuses into helium in the star's youth. Later, helium burns into carbon and oxygen. Then, in truly massive stars, oxygen, neon, magnesium, silicon, sulfur, and more in turn undergo fusion as the star approaches old age. This sequence of fusion reactions builds up the periodic table within the star, but it stops at iron. As we saw, once iron accumulates in the core, no further fusion can release energy. Without energy output to support it, the iron core succumbs to gravity and collapses, triggering a core collapse supernova. When a supernova explosion occurs, it not only liberates these pre-made elements by blowing the star apart, it also creates new ones in the heat of the blast. Consider the core collapse supernova of a massive star. As the shockwave rips through the star's layers, the extreme heat and flood of neutrons trigger a flurry of nuclear reactions in the surrounding material. In mere seconds, elements heavier than iron are synthesized via rapid neutron capture (E), a process called the R process. The collapsing core unleashes an enormous number of neutrons, and atoms riding the shockwave absorb these neutrons in rapid fire succession. These neutron-heavy nuclei then undergo radioactive decay into stable elements. In this way, elements like iodine, gold, platinum, uranium, roughly half of all elements heavier than iron, are created in the cauldron of a single supernova explosion. Meanwhile, in a Type Ia supernova, a different kind of nucleosynthesis occurs: the furious burning of carbon and oxygen into a range of intermediate mass elements, particularly a lot of nickel and iron. Type Ia supernovae are prolific producers of iron group elements. In fact, the iron that makes our blood red and the nickel and cobalt in steel are spread through galaxies largely by Type Ia supernovae. Without those explosions, iron, the heaviest element that normal stellar fusion can produce in quantity, would remain locked in stellar cores or white dwarfs. Supernovae act as cosmic salt shakers, scattering these elements into the galactic soup. Think of a supernova as a cosmic seed spreader. The heavy elements created over the star's life, and in its explosive death, are hurled into space at thousands of kilometers per second. In the aftermath, what was once the star's core might be a neutron star or black hole, but all its outer material, now enriched with a bouquet of heavy elements, mixes into the wider interstellar medium. Over millions of years, that gas will drift, cool, and mingle with other gas clouds. When new stars eventually form from those clouds, they inherit that enrichment. Planets condense from the leftover dust and gas around those new stars, and in some of those planets, life might one day arise, incorporating the atoms that were forged in a star long ago. To put it poetically, supernovae are the universe's way of taking matter cooked in one star's kitchen and delivering it as raw material for new worlds. In the early universe, before any stars had lived and died, there were only the lightest elements: hydrogen, helium, and trace amounts of lithium. The very first generations of stars were born from this pristine gas. Many of those first stars likely died in powerful supernovae that enriched their surroundings with the first heavy elements. Each subsequent generation of stars thus had more metals available. Our Sun was born from a cloud already seeded by countless prior supernovae. That's why Earth has an iron core and rich chemistry, and why life here can have elements like carbon, nitrogen, phosphorus, and so on. All those elements were gifts from stars that died before the Sun was born. Carl Sagan famously said, "We are made of star stuff." And this is not just metaphor, but scientific truth. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in the apple pie we might eat. These atoms were forged in stellar interiors and in the titanic explosions of supernova. We carry within us the ashes of long dead stars. Every time you hold a piece of gold jewelry or take a breath of air, you are touching remnants of a supernova's fury. In a very real sense, supernovae are our ancestors. They sculpted the elemental abundances of our galaxy. They made possible the chemistry that begot life. Realizing this connection can change the way we see a starry night. The sky is no longer just a beautiful backdrop. It's our ancestral home. We have stardust in our veins. Supernovae ensure that the universe is chemically rich and ever changing, rather than static and composed of only the simplest elements. A universe without supernovae would be a dull place. No rocky planets, no breath of air, likely no life. Having explored how supernovae forge the ingredients of planets and people, let us now examine what becomes of the stars themselves after the blast. What of the core that collapsed? That neutron, rich ball that was left behind? It may become one of the strangest objects in the universe. Let's meet the exotic corpses of massive stars, the neutron stars and black holes that emerge from the wreckage of supernovae. The corpses of stars, neutron stars, and black holes. After the immense explosion of a supernova fades, after the debris is cast into space, something often remains at the center, an ultra-dense stellar corpse, the condensed memory of the star that was. In the case of a core collapsed supernova, the core's collapse is halted by forces of quantum physics, leaving behind either a neutron star or, if the star was hefty enough, a black hole. These remnants are as fascinating as the explosions themselves, for they are among the strangest objects in the universe. Neutron stars, the spinning cinders. Imagine compressing the Sun, 333,000 Earth masses, into a sphere about 20 kilometers across, roughly the size of a city. The crush of gravity is so extreme that atoms cannot survive. Electrons have been rammed into protons to form neutrons, and matter as we know it is essentially transformed into a giant atomic nucleus. This is a neutron star. A sugar cube-sized amount of neutron star material would outweigh a mountain. The gravity at its surface is so strong that if you dropped a marshmallow from 1 meter above a neutron star, by the time it hit the surface, it would strike with the energy of an atomic bomb. These mind-bending facts belie the humble name, neutron star, but they are the reality of what a massive star's core becomes after a successful supernova explosion. Neutron stars often reveal themselves as pulsars. objects that emit beams of electromagnetic radiation that sweep around as the star rotates, like beams from a lighthouse. The first pulsar was discovered in 1967 by Jocelyn Bell. At first it was so regular that it was half jokingly nicknamed LGM-1, hinting at the intrigue it caused. We now know pulsars are rapidly spinning neutron stars with intense magnetic fields, whipping around perhaps dozens or hundreds of times per second. The Crab Nebula's heart, for instance, is the Crab pulsar, spinning about 30 times a second, a lighthouse flashing in the wreckage of the 1054 supernova. Every pulse we receive is a rotation of that tiny neutron star, which carries on the legacy of the once mighty star by flashing its cosmic heartbeat centuries after the star's explosive death. Some neutron stars are even more extreme, magnetars, with magnetic fields 1,000 times stronger than a typical pulsar, capable of emitting flares that can disrupt Earth's ionosphere from tens of thousands of light years away. These bizarre objects are variations on the theme of neutron stars, matter in its most compact, stable form, holding perhaps up to 2 or 3 solar masses in that ultra-dense sphere. They gradually cool and slow down over time, but for many millions of years, they can spin rapidly and power energetic emissions, effectively signaling their presence to the cosmos. In a very real way, a neutron star is the remaining core of a star, still there after the supernova, not shining by fusion, but often emitting energy as it slows down, the stellar core's ghost, left haunting the site of the explosion. Black holes, the silent tombs. If the collapsed core of a star exceeds a certain mass, not even the pressure of neutrons can halt the collapse. In that case, gravity wins absolutely, and the core continues to shrink beyond the neutron star stage. It effectively vanishes from view, leaving behind a gravitational well so deep that not even light can climb out. A black hole is born. What remains is an object perhaps only a few kilometers wide, but containing more mass than our Sun. An object with no surface, only a point of no return, called an event horizon. Inside that boundary, space, time is curved into a pit from which nothing that falls in can escape. The core of the star has become a literal hole in the fabric of reality. Black holes were once theoretical curiosities, sprung from Einstein's general relativity equations, and considered by some to be too absurd to be real. Today, we have overwhelming evidence of their existence. Many stellar black holes announce themselves indirectly, often by interacting with a companion star. Gas from the companion may spiral into the black hole, heating up and emitting powerful X-rays before it vanishes across the event horizon. Cygnus X1, an X-ray source discovered in the 1960s, was the first strong black hole candidate. It likely formed from a massive star's collapse. Now we know many such X-ray binaries harbor black holes. Additionally, the ripples of gravitational waves detected in the past few years by observatories like LIGO and Virgo have come from mergers of stellar mass black holes, offering yet another confirmation that these dark remnants are out there. To stand on the surface of a neutron star or near a black hole's horizon is to confront the ultimate victory of gravity. Time itself behaves oddly in these realms. A clock on a neutron star's surface would tick significantly slower relative to one far away due to gravitational time dilation. Near a black hole, that effect becomes even more extreme. Time essentially stops at the horizon from an outside perspective. These effects, though counterintuitive, have been measured in weaker gravity regimes and match our theoretical predictions. In simpler terms, a neutron star, or black hole, is the outcome of a star's final battle with gravity. The star's core, unable to hold itself up, imploded and then found a new equilibrium as one of these exotic objects. They are the cinders or tombstones left after the brilliant supernova fire has gone out. Yet they are far from inert lumps. Neutron stars can light up their surroundings with beams of radiation or intense magnetic fields, and black holes, when fed by infalling gas, can become the engines for powerful X-ray sources or micro-quasars. Even in death, these stellar remnants can profoundly affect their environment. When we gaze into the night with radio telescopes or X-ray eyes, we occasionally hear the ticking of pulsars or see the flickering high energy glow of accreting black holes. Each is a supernova after story, the quiet, persistent end note to a star's life. In the grand narrative, a massive star lives, explodes, and then either as a neutron star or black hole remains as a kind of monument. It's humbling to realize that the universe is littered with these tiny, dark remnants, hidden endpoints of countless stellar lives. We have now followed the star from cradle to grave, born in a cloud, shining steadily, dying in an explosion, and leaving behind a strange new object. Let us cast our eyes outward again to the expanding remnants of those explosions and see what becomes of the scattered star stuff itself. Supernovae do not merely vanish, they leave behind remnants that continue to glow and evolve, creating some of the most beautiful and intriguing sights in the cosmos. Ghostly echoes, supernova remnants. Long after the blinding flash of a supernova has faded from the sky, an ethereal apparition remains, the supernova remnant. These are vast, expanding clouds of debris, the scattered ashes of a star, still glowing from the energy of the explosion and the radioactive elements within. Supernova remnants are like cosmic smoke rings, beautiful, complex, and evolving over time, marking the spot where a star met its end. If we could watch a supernova remnant in fast forward, we'd see an almost spherical shockwave racing outward, plowing into the surrounding interstellar gas. Behind the shock front trails the tattered debris of the star, a mix of elements and newly formed radioactive isotopes, forming intricate structures as it interacts with itself and the environment. Immediately after the supernova, this cloud is extremely hot and shines brightly in X-rays. Over centuries and millennia, it expands and cools, beginning to radiate at optical wavelengths as well, and later in radio waves. Filamentary shapes appear, tangled ropes and sheets of gas shaped by magnetic fields and variations in density. One of the most famous remnants, the Crab Nebula, is a sight to behold even in a small telescope, a faint oval patch of light with subtle filament patterns. Long exposure photographs and modern space telescopes reveal those filaments in exquisite detail. Tendrils of glowing red, orange, where cooler gases like hydrogen and nitrogen emit visible light, interlaced with a bluish haze of electrons spiraling in the pulsar's magnetic field. The Crab Nebula is effectively powered from within by its pulsar. The neutron star's rotational energy keeps pumping out particles and fields that energize the nebula, making it shine far longer than it would from the explosion's initial heat alone. It's as if the remnant is a living organism with a beating heart that refuses to let the glow die out. Another remarkable remnant is Cassiopeia A. Although its originating supernova around 1680 was not widely observed, Cass A is a young remnant about 350 years old, and high-resolution images show an asymmetric, lumpy shell of gas about 10 light-years across. It's rushing outward at thousands of kilometers per second. By studying Cass A, scientists have gleaned insights into how the supernova explosion might have been irregular, not a perfectly symmetric blast, but one that ejected knots of material in some directions more than others. Cass A's debris is rich with elements like oxygen, sulfur, and silicon, clearly marking it as the remains of a massive star. In the center lies a faint neutron star, cooling in quiet isolation. The ghost of the star is not at rest. It's expanding and colliding with its surroundings, sending out shockwaves that heat the interstellar medium and even accelerate cosmic rays that zip through our galaxy and occasionally reach Earth. supernova remnants can be breathtakingly beautiful. The Veil Nebula in Cygnus, for example, is the remnant of a supernova roughly 8,000 years ago. It now spans about 3 degrees of the sky as a wispy lacework of ionized gas. Through a telescope, parts of it appear as delicate filaments, so thin and gossamer that one can scarcely imagine the violent event that created them. These filaments are shock fronts seen edge on, where the shell of the remnant is plowing into interstellar space and causing the gas to glow. What was once a catastrophic blast has, over millennia, become a faint, ghostly veil decorating the sky. Beyond their beauty, supernova remnants are profoundly important to the ecosystem of the galaxy. As the remnant expands, it sweeps up and stirs the interstellar medium, mixing the new heavy elements from the explosion into the cosmic clouds. This enriched material will one day become part of new stars and planets. The shock waves can trigger the collapse of nearby gas clouds, perhaps inducing new stars to form, so one star's death can sow the seeds for the birth of others. At the same time, remnants inject energy into the galaxy's gas, heating it and driving turbulent motions that can inhibit immediate star formation elsewhere. This feedback helps regulate how galaxies evolve, preventing them from turning all their gas into stars at once. Over tens of thousands of years, a supernova remnant will gradually dissipate. Its shock slows to the speed of sound in the surrounding medium and eventually merges with the general interstellar environment. By then, the heavy elements are well blended into the galactic reservoir. Only faint traces might remain, perhaps slightly higher concentrations of certain elements in that region of space, or cosmic ray particles that were accelerated by the remnant's shock still wandering the galaxy. Thus, a supernova remnant is the intermediate chapter of the story between the violent death and the eventual recycling of the star's substance into new cosmic structures. It's the long, fading echo of the supernova's shout. By reading the glowing wisps and shock fronts, scientists can decode details of the explosion, how fast the material is moving, what it's made of, and how it's interacting with its surroundings. Even long after a star has died, its remnant continues to tell its story. In every supernova remnant, we see a snapshot of change in action. They are elegant reminders that even after catastrophic destruction, there is quiet creation and transformation. The scattered atoms will someday cool and perhaps gather again in dark nebulae, ready to form the next generation of stars. In that way, a ghostly remnant is not an end, but a bridge to new beginnings. Stepping back from individual remnants, we consider the grand scale once more. Supernovae, whether near or far, serve as brilliant beacons in the cosmos. Their light and energy travel across vast distances, sometimes allowing us to measure and understand the universe itself. In the next section, we'll explore how these stellar catastrophes become cosmic lighthouses and what they have revealed about the space between the galaxies and the fate of the universe at large. Cosmic beacons, light across the universe. Supernovae are not only agents of cosmic recycling, they also serve as signposts on the grandest scales. When a star explodes, it becomes, for a few weeks, one of the most luminous objects in the universe. A single supernova can outshine an entire galaxy of billions of stars. This extraordinary brilliance means that supernovae can be seen across immense distances, allowing astronomers to use them as cosmic beacons or lighthouses. By observing supernovae in remote galaxies, we can measure those galaxies' distances and probe the expansion of the universe itself. Among all supernovae, the type Ia have proven especially valuable in this regard. Because a type Ia results from a white dwarf reaching a critical mass and undergoing a thermonuclear explosion, the amount of energy released is fairly uniform from one event to another. In more practical terms, most type Ia supernovae reach about the same peak absolute luminosity, like bulbs of nearly the same wattage. If we observe a type Ia in a distant galaxy and measure how bright it appears, We can compare that to the known true brightness and deduce its distance. A classic use of the inverse, square law of light. This is why Type Ia supernovae are termed standard candles. In the late 20th century, astronomers began using these standard candles to chart the universe. They painstakingly observed Type Ia supernovae in faraway galaxies, billions of light years distant. By doing so, they aimed to measure how fast the universe was expanding at different times in the past. The expectation was that the expansion should be slowing over time as gravity tugged on galaxies. But the supernova beacons told a different story. In 1998, two independent teams analyzing distant Type Ia supernovae made a shocking discovery. Those supernovae were dimmer than expected in a decelerating universe. The simplest explanation was that the expansion of the universe has been speeding up, an acceleration driven by some mysterious force or energy inherent to space itself, later dubbed dark energy. It was a revelation that earned the 2011 Nobel Prize in Physics for the team leaders. Think about that. By observing the dying flashes of stars in galaxies halfway across the observable universe, we gleaned insight into the fundamental behavior of the cosmos on the largest scale. Each supernova that appeared in those distant galaxies, tiny dots of light on telescope images, carried within it the information needed to trace the history of cosmic expansion. The lives and deaths of stars, recorded as brief flickers in the night, became evidence for a new ingredient of the universe that now appears to dominate its fate. Supernovae also help us measure distances closer to home and map the three-dimensional structure of the universe. Even before the discovery of cosmic acceleration, astronomers used Type Ia supernovae to refine the Hubble constant. By comparing distances from supernovae with the redshifts of their host galaxies, they calibrated the relationship between redshift and distance. This led to a better handle on the size and age of the universe. To this day, monitoring supernovae in distant galaxies remains crucial for improving our understanding of the universe's expansion history and for probing the nature of dark energy. Apart from cosmology, supernovae act as beacons that illuminate their local environment. As their light travels through space, it can be absorbed or re-emitted by any intervening gas or dust. By studying the spectrum of a supernova, we can detect absorption lines from elements in the host galaxy or in between galaxies. In one famous case, light from a distant supernova passed through the vicinity of a foreground galaxy cluster and was gravitationally lensed, producing multiple images of the supernova that reached Earth at different times. Astronomers observed one image of that supernova and, by understanding the lensing delay, successfully predicted when the second image would appear a couple of years later, and they saw it right on schedule. This kind of phenomenon turns supernovae into probes of the distribution of matter in the lensing clusters. Even without such exotic effects, every supernova in a distant galaxy provides clues about that galaxy, its composition, its star formation, history. When a massive star explodes in, say, a galaxy tens of millions of light years away, we detect it and thus learn that this galaxy is actively forming stars. Supernova surveys have catalogued thousands of supernovae in all types of galaxies, revealing patterns. For instance, Type II and Type IB C supernovae occur only in galaxies with ongoing star formation. You won't find a massive star supernova in a quiescent elliptical galaxy, because such galaxies no longer have massive young stars. On the other hand, Type Ia supernovae occur in both star-forming galaxies and old elliptical galaxies, since every galaxy has some population of binary white dwarfs or old stars that can produce them. The sheer number of supernovae now catalogued has allowed us to identify rare subclasses and see subtle differences. We've found peculiar types often by catching them in other galaxies. No two supernovae are exactly alike. Each explosion has its quirks, but they cluster into families that we can study statistically. And all of this has been possible because the universe provides an endless supply of distant supernovae, and we've developed the technology to monitor the sky systematically. Technology is rapidly advancing this field. The Vera C. Rubin Observatory in Chile, with its legacy survey of space and time, is expected to discover on the order of 10,000 supernovae per year in the coming decade. It will effectively make a high-definition movie of the optical sky, catching transient events like supernovae on a nightly basis. We will have supernova light curves and spectra in amounts previously unimaginable, likely uncovering new oddball explosions and further refining the use of supernova as cosmic yardsticks. There's also something profoundly moving about seeing supernova in distant galaxies. It drives home the point that the life and death of stars is a universal saga. When you see a tiny, bright dot on an image of a galaxy tens of millions of light years away, knowing it's the death throe of a star, possibly someone else's sun in that galaxy, you feel an intimate connection with a distant part of the universe. These events link us with other galaxies, not just in a physical sense, but in a narrative sense. The story of stars and supernovae is a thread that runs through the cosmos, binding our Milky Way to the remotest spiral. From the closest supernova observed with the naked eye in centuries to the farthest detected by our most sensitive telescopes, each is a flash of enlightenment across space and time. Through them, the universe has communicated its nature to us. They have been beacons not only of light, but of knowledge, guiding us to understand cosmic distances, the expansion of space, and the history of galaxies. We have now covered supernovae from the tiny scale of atomic nuclei in a collapsing core to the vast scale of the accelerating universe. It seems fitting, as we near the end of our journey, to reflect on what it all means, how the death of stars is connected to the existence of life, and what philosophical insights we can glean from the cycle of stellar death and rebirth.
Danger in the sky, the threat of supernovas.
Supernovae captivate us with their brilliance and enrich us with their stardust, but they also remind us that the cosmos can be dangerous. A star's death is not only a spectacle, it unleashes a storm of radiation and high-energy particles that can have profound effects on its surroundings. If such an explosion happened close enough to Earth, the consequences could be severe for our planet's biosphere. Have supernovae ever affected life on Earth? Could they in the future? These questions take us from cosmic wonder to an edge of concern. Fortunately, the odds of a supernova occurring very near Earth in our lifetimes are low. Our sun is not massive enough to explode, and among the nearest stars, none within the critical distance are likely to go supernova soon. The general consensus is that a supernova closer than about 25 to 50 light years could pose a serious threat, primarily by bathing Earth in intense high-energy radiation and a barrage of cosmic rays. The immediate effect of such radiation on Earth's atmosphere would be to erode the ozone layer that shields us from the sun's ultraviolet rays. With the ozone layer damaged, harmful solar UV would flood the surface, potentially causing mass die-offs, especially in marine ecosystems where plankton, the base of the food chain, are vulnerable to UV. Scientists have searched for fingerprints of past supernova effects on Earth. One intriguing find lies in ancient seabed deposits. An excess of the radioactive isotope iron in sediment layers dated around 2,003 million years old. Iron-60 is produced in supernovae and has a half-life of 2.6 million years, so finding it on Earth's surface implies a relatively recent nearby supernova. Indeed, some studies suggest that one or more supernovae occurred about 2.5 million years ago at 150 light-years away, possibly affecting Earth's climate or contributing to minor extinctions. Another study links increased radiation levels to a minor extinction at the end of the Pliocene epoch, speculating a supernova as a cause. While these connections remain under investigation, they highlight that Earth is not completely immune to astrophysical events. If a supernova happened, say, within 30 light-years, The radiation pulse could cause a mass extinction by wrecking the ozone layer and bombarding life with UV. The geological record does show some unexplained extinction events that some scientists have playfully speculated might be due to nearby gamma, ray bursts, or supernova. Which nearby stars could pose such a threat? The good news is, none of the very closest stars are of the type to explode soon. The nearest massive stars are dozens to hundreds of light years away. Betelgeuse, the red supergiant in Orion, often comes up in discussion. It's about 650 light years away. When Betelgeuse does explode, it will likely put on a spectacular show, potentially bright enough to see in daytime, but it's too distant to harm Earth aside from perhaps some subtle effects on our upper atmosphere. Candidates often mentioned include stars like Antares, or more significantly, a star system called IK Pegasi, which includes a white dwarf that could become a Type Ia supernova in the far future. However, by the time IK Peg's white dwarf accretes enough mass from its companion to explode, it will likely have drifted farther from us. Another potential danger comes from gamma, ray bursts, extremely energetic jets that can accompany certain supernova-like events, especially the collapse of an especially massive, rapidly rotating star into a black hole. If a gamma ray burst were pointed directly at Earth from a few thousand light years away, the focused beam of gamma radiation could be devastating. Even from much further than the supernova's general radiation would be dangerous. Fortunately, such GRBs are rare, and the Milky Way is big. No known GRB progenitor is close enough and aimed at us to cause concern at present. One speculative idea is that a GRB might have caused the Ordovician mass extinction 450 million years ago, but this remains unproven and perhaps unprovable. So, while the risk is never zero, it appears that at this moment in cosmic time, Earth is not in the crosshairs of any nearby supernova candidates. We can be grateful for the margins the cosmos has given us. We live bathed in the gentle radiation of a stable, middle-aged star, far from the volatile furnaces that would endanger us. Even so, the concept of supernova threats has spurred some interesting science. For instance, astronomers have surveyed the sky for traces of past supernovae and keep tabs on the massive stars within a few hundred light years. We are effectively monitoring the environment of our solar neighborhood for potential supernova weather. It's sobering to think that events light years away can influence life on a planet, but it's also part of the dynamic nature of the universe. Human civilization might someday have detectors that could provide an early warning if a nearby star's core collapses. We already have neutrino detectors that would give us a few hours' notice of a supernova. Neutrinos escape the collapsing core before the light from the explosion gets out. Thankfully, the notice will likely be for an exciting show, not a doomsday event. Supernovae, then, are a double-edged sword, creators and destroyers. They likely helped enable life by forging elements and shaping environments, but in rare cases, they might also snuff life out. The very cosmic events that made our existence possible could, under different circumstances, pose a lethal threat. For us, the bottom line is that we should continue to watch the stars, both out of scientific curiosity and for prudent awareness. The night sky is mostly peaceful, but it has its violent moments. Knowing that our planet has likely survived nearby supernovae in the past, we carry on under the stars with both awe and respect. Now that we have contemplated the dangers supernovae might pose, let's turn our attention to some of the most extreme kinds of stellar explosions known, those that push the very limits of power, and those curious cases where a star's death might not produce much visible light at all. Extraordinary explosions, superluminous and pair, instability, supernovas. Just when we might think we've seen it all, the universe surprises us with stellar explosions, even more powerful or peculiar than the standard supernovae we've discussed. In recent decades, astronomers have identified a class of supernovae so luminous that they outshine normal supernovae by 10 or even 100 times. These are the superluminous supernovae. cosmic blasts so bright we can detect some from the early universe, billions of light years away. On the other end of the spectrum of weirdness are pair instability supernovae, theorized explosions of the most massive stars that completely obliterate the star. Both types push the boundaries of how stars live and die. Superluminous supernovae. Imagine a star explosion so bright that for a time it can outshine an entire galaxy. In 2007, astronomers observed a supernova, SN 2006 GY, in a relatively nearby galaxy that was over 100 times more luminous than a typical Type II supernova. It stayed bright for many months. This was one of the first confirmed superluminous supernovae, and it left astronomers both excited and puzzled. What could cause such an extraordinary outburst? Since then, many more SLSNE have been found, often in small, distant galaxies with very active star formation. These events reach absolute magnitudes of 21 or 22, meaning at peak, they can be 10 to 50 billion times the brightness of the Sun. What powers such brilliance? In some cases, it may be a central engine, perhaps a newborn magnetar left by the explosion, which pumps energy into the ejector as it spins down. As the magnetar's immense rotational energy is transferred to the expanding gas, it keeps the gas hot and glowing much longer and brighter than usual. In other cases, the cause might be the collision of the supernova's ejector with a dense shell of gas around the star, a shell the star shed in a dramatic eruption before it exploded. The kinetic energy of the explosion gets converted into light in this collision, a bit like a cosmic traffic accident, producing a brilliant flare. SN 2006 GY, for example, is thought to have been such a case. A very massive star might have thrown off a large amount of mass in an eruption or series of eruptions, and then shortly after, its core collapsed and it exploded. The supernova blast wave slammed into the previously expelled gas, producing an extremely bright, long-lasting flash. These types of interactions are classified as Type II supernovae, and indeed, some events observed historically as supernova imposters, where a star suddenly brightened but didn't die, were likely these precursor eruptions. The prime example is Eta Carinae, which in the 1840s became one of the brightest stars in the sky for a few years without exploding. It ejected a massive bipolar nebula and survived. Eta Carinae remains with us, albeit much dimmer now, and is still a ticking time bomb for a future supernova. Its great eruption was a supernova imposter, a false alarm, one might say, hinting at the chaos within the star. Many superluminous supernovae seem to involve stars that had similarly big eruptions shortly before final collapse, essentially setting themselves up for an especially luminous demise. Pair instability supernovae, when stars obliterate themselves. Now consider the upper limit of stellar mass, say a star with 150 to 250 times the mass of our Sun, something only likely to form in pristine conditions. In such a monster star, during its late evolutionary stages, a strange thing can happen. The core becomes so hot that the energy of gamma ray photons being produced start spontaneously converting into matter and antimatter pairs. This process robs pressure from the core. The sudden drop in pressure causes the core to contract dramatically, the pair instability. This contraction raises temperatures even further, igniting runaway fusion. If conditions are just right, this results in an explosive thermonuclear burning that unbinds the star completely. A pair instability supernova. The star is blown to smithereens. No black hole is formed, because even the core is blasted apart in the explosion. Pair instability supernovae are purely theoretical for now, though there are candidate events. They would be extremely luminous and long-lasting because the star is being burned and ejected entirely. SN 2007 BI is an example that was proposed as a pair instability supernova.
It occurred in a small, distant galaxy and was exceptionally bright and slow to fade, with indications that tens of solar masses of nickel were synthesized. If indeed it was such an explosion, it means somewhere out there, a star of around 200 solar masses lived fast and died in a unique way, completely annihilating itself. There are also pulsational pair instability scenarios, where a massive star doesn't quite blow itself up in one go. Instead, the pair production instability causes a partial collapse and eruption that throws off the star's outer layers but leaves the core intact. The star survives that pulse for a while, until it later perhaps pulses again, or eventually the core collapses to a black hole once enough mass is lost. These pulses can also produce bright transient events. The recently observed oddball IPTF 14HLs, a star that appeared to undergo multiple explosions over a few years, might be an example of a pulsational pair instability event. It baffled astronomers by acting like a supernova that just wouldn't finish dying, brightening, fading, then brightening again 5 separate times over more than 2 years. One hypothesis is that it was a star, perhaps 100 solar masses, that had a series of internal pulsations, blowing off shells of material in eruptions, but not yet destroying its core. Eventually, perhaps that star will finally undergo core collapse and explode for good. But in the meantime, we witnessed a zombie supernova. This shows how even in death, some stars can take an unusual path. Hypernovae and gamma-ray bursts. While on the topic of extremes, it's worth mentioning the term hypernova, often used to describe an exceptionally energetic supernova, typically one associated with a long-duration gamma-ray burst. In the 1990s, as gamma-ray bursts were being localized to distant galaxies, it became clear that at least some long GRBs were linked to the deaths of very massive stars. Essentially, if a very massive star collapses and forms a black hole, and if it has enough angular momentum and magnetic fields to produce collimated jets, we get a GRB, a blast of gamma, rays shooting out along the rotation axis of the star. If Earth lies along the path of one of those jets, we see a GRB. Meanwhile, the star's remaining material still explodes in what we would call a supernova, specifically a type IC, since the star has likely shed its hydrogen and helium envelopes. These explosions can be extremely energetic, because the jets deposit additional energy into the ejector. SN 1998BW, coincident with GRB 980425, was the first strong case of a GRB-related hypernova. It was unusually luminous in radio and had very high expansion velocities. Since then, a few dozen GRB supernovae have been observed, confirming that at least some of the brightest explosions come from this engine-driven mechanism. All these extraordinary explosions, superluminous supernovae, pair instability events, pulsational multi-explosion stars, and hypernovae with gamma-ray bursts, demonstrate the incredible range of fates that befall the most massive of stars. They are relatively rare, but they are crucial to testing the limits of physics. They show us what happens in stars at the upper mass limits, how the first stars might have died, and how the most extreme energies in the stellar regime are released. These explosions also stretch our vocabulary and our understanding. They have forced astronomers to expand theories, to include magnetospin, down energy in light curves, to consider matter-antimatter pair creation in stellar cores, to account for asymmetric jets ripping a star apart. They are the flamboyant outliers of the supernova family, but often in those outliers lie insights into regimes of nature we cannot replicate on Earth. On the flip side, just as some stars explode more spectacularly than expected, some massive stars may fail to explode at all, collapsing into darkness with hardly a trace. Not every stellar death results in a bright supernova. Next, we will explore these enigmatic failed supernovae, cases where a star's core collapses into a black hole and yet produces little or no visible explosion. The ones that failed, when stars collapse without a bang. Throughout our journey, we have assumed that when a massive star's core collapses, a titanic explosion, a supernova,
inevitably follows. But nature has a more silent ending on the menu as well. Sometimes a star can die with hardly a whimper. In these cases, the core implodes, and instead of blasting the star's outer layers apart, it simply pulls them inward, swallowing the star into a newly formed black hole. These are the so-called failed supernovae. For a long time, failed supernovae were speculative. Simulations of core collapse hinted that if the conditions weren't just right, say, if the shockwave lost too much energy and couldn't be revived by neutrinos, the infalling star might never explode. The core would become a black hole, and aside from perhaps a brief cough of energy, the star would just disappear. What would that look like to an observer? Perhaps a star would brighten a little as the core started to collapse, then fade away forever. In recent years, astronomers have actually been looking for this phenomenon. How do you catch a star failing to explode? One approach is to watch many supergiant stars in nearby galaxies over time and see if any simply vanish. Remarkably, one candidate has emerged. A star in galaxy NGC 6946 was observed to brighten modestly in 2009, and then by 2015, it had vanished from optical view. It was a hefty red supergiant before it disappeared. This object, nicknamed N6946 BH1, likely underwent core collapse and formed a black hole without a successful supernova. There was a small burp of light, a sort of mini explosion or outburst, when it brightened in 2009, but no big supernova explosion followed. The star just became a memory, detectable now only as a faint infrared source. It appears we observed a failed supernova in real time, the first of its kind. One hypothesis is that the core of the star collapsed directly into a black hole, and the weak shock generated wasn't enough to eject the star's outer layers. Instead, most of the star fell into the black hole. The small amount of energy released by the core collapse created a faint transient event. Indeed, some very massive stars might shed a bit of their envelope or produce a low-energy explosion, but still end up mostly collapsing, what we call a fallback supernova or failed supernova. Why would a star fail to explode? It likely depends on mass and the detailed physics of the core collapse. It's thought that stars above roughly 17,020 solar masses might have a harder time exploding. If the core forms a black hole quickly, it can swallow infalling material so fast that the shock is smothered. Alternatively, if the star has a very large, extended envelope, the shock might stall out in that envelope without unbinding it. The evidence is mounting. We see fewer supernovae from the very most massive red supergiants than expected, perhaps because those stars quietly collapse instead. It seems quite plausible that many black holes in our galaxy formed without a bang. What would a failed supernova look like up close? Suppose we were watching a massive star in its final days. We might see it start to dim and brighten irregularly as it undergoes convulsive nuclear burning of silicon. Then, perhaps, a sudden but short-lived glow, the outer layers briefly heating as the core collapses and maybe a weak shock travels outward. The star might expel a small fraction of its material. Neutrinos would flood out, possibly the only strong cry of the dying star. Then, the light fades. The star's surface material, which didn't get enough of a push to escape, rains back down into the black hole. To an optical telescope, the star simply vanishes. In NGC 6946, astronomers literally have before and after images. The star was there, and then it wasn't. If such a failed supernova happened in our galactic neighborhood, we might detect it not by light, but by an outpouring of neutrinos, ghostly particles released by the imploding core without a bright optical display. Future neutrino observatories could potentially catch these subtle signals of a star collapsing directly into a black hole, giving us a heads up even when the star itself disappears in darkness. Failed supernovae are a chilling reminder that not all stars go out with a glorious finale. Some simply cease to shine, leaving no glowing remnants, just an invisible gravitating mass. If massive stars can collapse quietly, there might be many dark corpses drifting in galaxies, undetected unless they interact with a companion or surrounding gas. An entire population of silent black holes could be lurking, each marking a life that ended without fanfare. Even so, such a death would not be entirely without a signal. A collapsing star still floods its core with neutrinos and rattles space-time with gravitational vibrations, even if no light escapes. Future neutrino observatories and gravitational wave detectors might pick up these subtle clues of a failed supernova, alerting us to a cosmic death that optical telescopes would miss entirely. The search for failed supernovae continues. With more years of data and more eyes on the sky, we hope to better quantify how often stars vanish without an explosion. It's an important piece of the puzzle of stellar evolution. It affects how many supernovae we count versus how many black holes we expect, and it tells us about the upper limits of how a star can die. We have journeyed now through nearly every twist and turn in the saga of stellar death, from spectacular hypernovae to silent collapses. All that remains is to step back and reflect on the grand picture one more time. Why do supernovae matter on the deepest level? What do they mean for us, living on a small planet around an ordinary star? In our final section, we consider the philosophical reflections that supernovae inspire. How, in their death, stars sow the seeds of new life, and how we, in turn, owe our existence to these cosmic catastrophes.
Epilogue. From death comes life.
We have traveled among giant stars and witnessed their demise. We have walked through cosmic time to see how each supernova, in destroying a star, contributes to the creation of something new. Now, at the end of our journey, we pause and look back at the grand tapestry we've been part of. A profound pattern emerges. In this universe, death is not simply an end, but a transformation. The death of stars is intimately linked to the birth of everything we hold dear. Consider the atoms that compose our bodies. Every breath we take, every glance we cast at the stars, we do so with atoms that were once inside of stars. Many inside stars that blew themselves apart long before the Earth existed. It took the violent sacrifice of countless stars to sprinkle the cosmos with carbon, oxygen, iron, and the rest of the periodic table. Only then could the clouds that formed our sun and Earth have the ingredients to build rocky planets and living organisms. In a very literal sense, we are the children of supernovae. Each one of us is a composite of stardust, forged in stellar hearts and scattered in stellar graves. This truth carries deep poetry. The universe has a cycle akin to the seasons. Stars are born, live gloriously, and die. From their remains, new stars take form. Out of destruction comes creation. It is a cycle that has been ongoing for billions of years, gradually enriching the cosmos and increasing its complexity. When we look at the night sky, we see the gleam of stars that will one day cease to exist. Some will quietly fade, others will end in spectacular explosions. Yet from their ruin, new worlds may one day blossom. Perhaps somewhere in our galaxy, a supernova exploding today is seeding a nebula that, in 5 billion years, will give rise to a star and planets, and perhaps life and consciousness that will look up and wonder as we do. There is a powerful philosophical echo here, impermanence and renewal. Stars, for all their immense power and longevity compared to our lives, are not eternal. They are born from dust and gas. They return to dust and gas. But in that returning, they fertilize space for new stars. The cosmos recycles itself. Endings are not only terminations, they are also beginnings in disguise. A supernova is an ending for a star, but the beginning of a nebula, the beginning of new chemical dispersal, the potential beginning of future life cycles. We humans, existing on our small planet, owe our existence to this grand and sometimes violent cycle. Perhaps counterintuitively, we owe our lives to explosions so distant in space and time we cannot name the sources. A star had to die for you to live. And not just one star, many. The gold in your jewelry, the iodine in your thyroid, the calcium in your teeth, these probably came from different supernovae scattered across the Milky Way over the past 10 billion years. You are an amalgam of stellar legacies. Realizing this connects us intimately to the cosmos. The boundary between us and the universe blurs. The universe is within us, literally. When ancient people saw supernovae, they often imbued them with divine or mystical significance. Today, through science, we see no less magic. If anything, the magic is amplified by understanding. Knowing that a point of light is a star ripping itself apart, and that such events made the world we know possible, adds layers of meaning to that transient star in the sky. In a way, we can view supernovae as the universe's way of keeping life possible. A universe without supernovae would be static and impoverished in elements, perhaps devoid of complex chemistry and life. Supernovae inject dynamism. They ensure that the universe doesn't stagnate, that material cycles through different forms. Out of the quiet, cold hydrogen of the early cosmos, supernova helped cook up the rich, warm complexity of planets and living organisms. As we conclude our cosmic journey, let's picture one more scene. We stand on a hill under a clear night sky. Above us, the Milky Way arches, a river of starlight. We know now that scattered among those stars are supernova remnants, the ghosts of long-dead suns, and perhaps a few stars that even now, as we watch, are living out their final moments, soon to explode. We feel the gentle night breeze, we hear the quiet of Earth, but we are aware of a colossal, ongoing drama playing out in silence overhead. One of those pinpoints of light might suddenly flare bright in our lifetimes, a nearby supernova gifting us a celestial spectacle, and while we gaze in awe, perhaps a being in another star system far away might at that same moment witness our sun as just another pinpoint in their sky, not knowing that around it a species capable of reflection and gratitude has arisen, thanks in part to ancient supernova. The cycle of stellar life and death is far grander than us, yet we find our own story within it. It instills humility. We are small and our lives flicker more briefly than any star, but also great connection. We are a way for the cosmos to know itself, born of its very fires. When a supernova's light reaches our telescopes after traveling for centuries or millennia, it is almost as if the universe is telling us its story, whispering through the night. See, this is how I renew myself. This is how, from death, I create life. And so, the next time we look up at the stars, we can remember that we are part of this cosmic story. The iron in our blood was once in the core of a massive star that died in a blaze of glory. The oxygen we breathe was forged in the belly of stars and spread by supernova winds. We are the universe, made conscious. We are star, stuff contemplating the stars. Supernovae are chapters in the universe's story, dramatic, violent chapters that nonetheless lead to creativity and rebirth. We began with cosmic death and rebirth. We end recognizing that they are one and the same. In the grand cycle of the cosmos, destruction and creation are intertwined. The universe evolves through this cycle, and we are one expression of its continual rebirth. In understanding supernovas, we understand ourselves a little better. Ephemeral, yet inextricably connected to eternity, fragile yet born of explosions, finite yet integral to an infinite cosmic cycle. The stars have died to give us life, and in their memory,
We live on and wonder, adding our own chapter to the saga of the cosmos.
In the silent emptiness of space, a star dies. One moment it shines as a distant pinprick in the darkness. The next, it erupts in a soundless flash of light that briefly outshines an entire galaxy. A titanic explosion unfurls in utter silence. No roar, no crash, for in the vacuum of space there is no medium for sound. It is a cosmic firestorm seen across light years, a brilliant beacon of death that appears without warning and vanishes just as quickly. For a few fleeting weeks, this single dying star pours out more light than billions of suns, blazing so brightly that if we were watching from a nearby world, it would paint shadows on the ground and outshine the night's full moon. Yet there is only silence. The star's final scream is in light, not sound. An immense outpouring of energy racing outward through the dark, telling anyone who cares to look that a star's long life has ended in cataclysm. What are we to feel, witnessing such a violent cosmic death? There is terror in the idea. A star, an object of almost eternal constancy in our sky, can explode without mercy. But there is also awe. In that silent explosion, we sense power beyond comprehension. The death throes of a sun many times larger than our own, unleashing energy in a few seconds that our sun will not emit in 10 billion years. Here is a celestial paradox, an event at once beautiful and destructive. A supernova, as astronomers call it, is the most brilliant of stellar fireworks. An eruption of light so powerful it can be seen across the universe. It is nature's way of shouting across the cosmos, a final cry of a dying star that echoes in starlight rather than sound. We watch in reverence, hearts humbled, for this silent, stellar eruption is more than just an ending. It is a moment of cosmic rebirth, a paradoxical creation forged by destruction.
The universe we will find is full of such paradoxes.
But how can a star, a colossal ball of plasma that has shone for millions of years, simply explode? What chain of events leads to this soundless flash in the sky? To answer these questions, we must journey into the heart of that star, into the forces and fires that sustain it, and ultimately into the tragedy that ends its life. Only then can we understand why this cosmic violence is not an empty tragedy, but a necessary drama that creates new worlds and even life. So let us venture now into the story of a star's life and death, a story written in the language of astrophysics and nuclear fire, yet rich with poetic grandeur, the story of a supernova. Imagine a star many times more massive than the Sun, born in a nebula of gas and dust. For eons, it has burned brightly, converting simple elements into heavier ones in a relentless alchemy. In its core, hydrogen, the simplest of all elements, fuses into helium, releasing the energy that makes the star shine. This process of fusion is the star's lifeblood, a delicate balance between pressure and gravity. Deep in the core, the outward push from fusion generated heat fights against the inward crush of gravity. As long as there is fuel to burn, the star maintains this equilibrium, shining steadily in the firmament. But stars, like living things, have cycles. Our massive star eventually exhausts the hydrogen in its core after millions of years of brilliant stability. Gravity, ever patient, begins to gain the upper hand. The core contracts and heats up until a new fusion fire ignites. Now, helium fuses into carbon and oxygen. The star has entered old age, swelling into a bloated giant. If we could see it up close, we would find its appearance transformed, often into a red supergiant, a star swollen to hundreds of times its original size. Its outer layers cooled and ruddy. Inside, however, the core burns hotter and hotter as it fuses heavier elements in turn. Shells of fusion surround the core like the layers of an onion, each shell burning a different element. Closest to the center, carbon fuses into neon. In a shell above, neon burns to magnesium and oxygen. Above that, oxygen fuses into silicon. Each stage produces the fuel for the next, and each stage of fusion burns faster than the last. What once took millions of years, burning hydrogen, gives way to shorter phases. Helium burning lasts a fraction of that time, carbon burning perhaps only centuries, oxygen mere months, and finally silicon burning might last only days. The star is living on borrowed time, rushing through its life's finale at breakneck speed. Layer by layer, like a great cosmic onion, the star builds up a core of iron deep in its center. Iron. This is a fateful element in the life of a massive star. For all the previous fusible fuels, hydrogen into helium, helium into carbon, and so on, fusion released energy. This energy held up the star's weight, staving off gravity. But when fusion creates iron, the game changes. Fusing iron does not release energy, it consumes it. The atomic nucleus of iron is the most tightly bound of all common elements. You cannot fuse iron into something heavier without paying an energy price. And so, as iron accumulates in the core, the star is unknowingly building a bomb at its center, a gravitational time bomb. With no more energy to be gained from fusion, there is no outward pressure that can be won from turning iron into heavier elements. The stellar core, once a powerhouse of light, becomes a dead weight of iron atoms. In the star's final moments, the iron core grows to a critical mass. Imagine a sphere of iron as large as Earth, but containing nearly the mass of our Sun, buried at the center of a star hundreds of millions of kilometers across. This core is supported only by the desperate pressure of electrons jostling in the iron nuclei, a quantum pressure, holding collapse at bay like an overloaded spring. But as the iron core's mass approaches a limit E, even this exotic electron pressure cannot hold back gravity. The core has run out of road. In a fraction of a second, it collapses. Gravity slams the core inward with incredible force, and nothing in nature can stop it. At the center of the star, densities soar and temperatures spike to billions of degrees. Iron nuclei disintegrate. High-energy photons smash iron atoms into fragments of helium, protons, and neutrons in a process called photodisintegration. Electrons are forced into protons, turning them into neutrons and releasing a flood of neutrinos. The core, in effect, is utterly breaking down, and in the span of a heartbeat, it implodes from a sphere the size of a city to an ultra-dense ball of neutrons only a few kilometers across. Gravity has won. The core is now a neutron star, an object so dense that 1 teaspoon of its material would weigh billions of tons on Earth. If the star is extremely massive, the core's collapse may not stop even there. It can continue into an infinitesimal point, a newborn black hole. For an outside observer, this moment is invisible. It happens hidden in the star's interior, but its consequences are about to burst forth. As the core collapses, it reaches fantastical densities, even comparable to an atomic nucleus. At that point, the collapse rebounds. The core's inner region stiffens abruptly, and the infalling material crashes against this hard stop. The result is a shockwave that begins to travel outward. Think of it like a sudden jolt. The core, having imploded, bounces slightly and sends a powerful pressure wave racing up through the star's layers. Yet even this might not be enough to blow the star apart. The shockwave expends tremendous energy, ripping apart iron nuclei in its path, and it can stall within the star as it encounters the overlying heavy layers. Here, the ghostly heroes of our story emerge, neutrinos. These nearly massless, elusive particles were released in staggering numbers during core collapse. A flood of them pours out of the core, carrying away the energy of gravity's triumph. In fact, 99% of the energy of the collapse is released as neutrinos, an almost inconceivable torrent of invisible particles. Under normal circumstances, neutrinos hardly interact with matter at all, but the sheer intensity of the neutrino blast from the collapsing core is unprecedented. In that brief moment, the core shines with neutrinos more powerfully than a billion suns shine with light. As the shockwave stalls, these neutrinos streaming outward deposit a fraction of their energy into the star's layers, rejuvenating the shock. It's as if an army of ghosts all struck in unison, delivering a final push to blow the star apart. A deafening silent roar in neutrinos propels the shockwave outward again. Within milliseconds, the core has transformed from a quiet iron ball into an engine firing out neutrinos and launching a shock front through the star. Now the doomed star's outer layers finally feel the effects. A ferocious blast wave races outward from the core, plowing through each overlying shell of elements. The star's immense envelope, hydrogen, helium, carbon, oxygen, all the layered elements built up over its life, is violently ejected. The shock heats the stellar material to incandescent temperatures, so as it blows out to space, it begins to glow brilliantly. The star is literally tearing itself apart from the inside. Within hours, the shock reaches the star's surface. The once stable star has become an expanding fireball. To any distant onlooker, this is the moment the star suddenly brightens by orders of magnitude, announcing the supernova. The dying star, which may have been a modest point of light before, now becomes something like a miniature galaxy in appearance, a single point shining with the luminosity of billions of suns. For a brief time, this one star's explosion can rival the brightness of an entire Milky Way of stars. Imagine it, a pinpoint of light in the sky outshining every other star in its galaxy, pouring out energy at an impossible rate. In one supernova, more energy can be released than our sun will radiate over its entire 10 billion year lifetime. The numbers defy imagination. The exploding star's luminosity can reach tens of billions of times the sun's output. Seen from a nearby planet, the night would turn into day for weeks. Even from thousands of light years away, such a supernova might be visible with the naked eye, as has happened at a few points in human history when supernovae in our galactic neighborhood briefly appeared as new stars in the sky. The Chinese, over 2 millennia ago, recorded a mysterious guest star that shone for months where no star had been before. Medieval astronomers, too, were astonished by sudden stars that could even be seen in daylight. All of these were supernovae, the spectacular deaths of distant suns, flaring into visibility across the void. In these moments of peak brilliance, the supernova is a mesmerizing sight. The star's outer layers hurtle into space at thousands of kilometers per second. A spherical tsunami of gas racing outward. The material glows from the immense heat of the explosion, producing an expanding shell of radiance. If the star was a red supergiant before it exploded, the shock may take some time to break out, and the supernova's light will then linger with a gradual decay, sometimes showing a plateau of brightness as its expanding hydrogen-rich envelope shines. If the star was a blue supergiant, more compact and hotter, the explosion might rise and fall faster, perhaps with an initial burst of high-energy radiation. Different stars produce different light curves in their death. Some supernovae maintain peak brightness for weeks, whereas others fade more quickly. In all cases, however, the spectacle eventually wanes. The enormous blast, having expended its energy, sees its debris cloud expand, thin out, and cool. Over months, the supernova's visible light diminishes, often transitioning to a dim nebula of glowing embers. But in those first days and weeks, the radiance is unrivaled. The supernova floods the spectrum with light, from energetic X-rays and ultraviolet flashes generated at shock breakout to the optical light that we see with our eyes, and onto infrared and radio waves as the ejector plows into surrounding space. It is a multi-wavelength beacon proclaiming a star's demise. Not every star ends this way. Only those of sufficient mass die in such spectacular fashion. Stars born with more than about 8 times the Sun's mass are destined for these core collapse supernovae. Our Sun, by contrast, will never explode. Far in the future, it will swell into a red giant and then gently shed its outer layers to form a planetary nebula, leaving behind a dense ember called a white dwarf. But massive stars live fast and die young. They burn through their fuel quickly and then explode, as we have seen. The supernova we've described, the collapse of a massive star's iron core, is one major type of stellar death. Yet intriguingly, there is another very different way to trigger a supernova. Not all stellar explosions come from a single massive star collapsing. Some come from a more subtle kind of stellar doomsday, a runaway nuclear detonation on a white dwarf star. In binary star systems, 2 stars orbiting each other, it sometimes happens that one star is a white dwarf, the tiny, dense remnant of a sun-like star, and it begins stealing matter from its companion. If the white dwarf gains enough mass, it can reach a critical threshold at which the pressure and temperature in its core ignite a furious wave of nuclear fusion. In a matter of seconds, carbon and oxygen inside the white dwarf detonate in a thermonuclear blaze. The white dwarf is blown to bits in a special kind of supernova explosion. Astronomers call this a Type Ia supernova, a thermonuclear supernova, and it differs from the core collapse supernova of a massive star. There is no iron core collapse to a neutron star. Instead, a white dwarf is completely destroyed by an uncontrolled fusion reaction. This too produces a dazzling burst of light and ejects star material into space, though the mechanism is fundamentally different. Type Ia supernovas tend to have very consistent brightness because they all explode when the white dwarf hits that same critical mass. They have proved immensely useful as standard candles for measuring cosmic distances. Their predictable luminosity allows us to gauge how far away they are by how bright they appear. But beyond their utility, they are yet another dramatic path for stardust to be scattered through the galaxy. Thus, the cosmos gives us 2 grand pathways to supernova: the implosion of a massive star's core and the detonation of a dead stellar core in a binary system. In the first, a giant star dies and leaves behind a neutron star or black hole. In the second, a small degenerate star is utterly obliterated, leaving no compact remnant at all. Both types scatter the star's elements into space with explosive force. Both are extremely luminous, though the details of their light differ. Astronomers distinguish them in observations by their spectra. Core, collapse supernova show signatures of the elements in their progenitor's atmosphere, whereas Type Ia supernovae lack hydrogen and instead show strong silicon, calcium, and iron lines from the white dwarf's incinerated interior. But to the eye, all these explosions look somewhat similar. A new star, like beacon, appears, shines intensely for a time, then fades. It is only by dissecting the light with telescopes and spectra that we uncover the tale of their origin written in the starlight. Whichever the type, a supernova is far more than an ending. As the exploded star's debris billows outward, it carries a priceless cargo, newly forged elements. In the ferocious furnace of the supernova, and in the final stages of the star that led up to it, nuclei of atoms have been fused into heavier forms. All the elements, heavier than hydrogen and helium, the carbon in your cells, the oxygen in the air, the calcium in your bones, the iron in your blood, were forged in stars and unleashed by supernovae. In fact, many of the heaviest elements are created during the supernova itself, in the extreme neutron-rich environment of the explosion. When that massive star's core collapsed and then blew apart, it created conditions for a rapid fusion of nuclei, a process scientists call the R process, which can build rare heavy elements like gold, uranium, iodine, and others that normal stellar burning could not produce. The hurricane of nuclear reactions unleashed in a supernova forge an array of new atomic nuclei. Then the explosion flings these atoms out into space, seeding the galaxy with the raw material for future stars, planets, and life. Think about what this means. Every atom of oxygen you breathe, every atom of carbon in your muscles or calcium in your teeth, was cooked up in the heart of a star and scattered across space by a supernova. Without supernovae, those elements would never have found their way into new generations of star systems. Without supernovae, life would not be possible. As one NASA science summary starkly puts it, the heavy elements that make our world solid and our bodies functional, iron, calcium, carbon, nitrogen, all trace their origins to stellar furnaces and explosive deaths. A supernova is thus not merely the death of a star. It is a cosmic resurrection of its substance, dispersing enriched matter into the galaxy to become the stuff of new celestial bodies. In the aftermath of a supernova, the expanding remnants of the star mix with the interstellar medium, enriching it. Over time, this debris might cool and collect into clouds, and those clouds can collapse to form new stars and planets. Every supernova is both an end and a beginning. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were brewed in the nuclear hearts of long, dead stars and cast into the galaxy by supernova explosions. We truly are made of stardust, born from stellar death. As the supernova's gaseous remnants expand and sweep through space, they shock and compress the clouds of interstellar gas they encounter. The blast wave from one star's death can trigger the birth of others. When the shock front slams into a cold molecular cloud, it can squeeze parts of it enough to start gravitational collapse, lighting new stars like kindling sparked by a flame. In this way, supernovae participate in a grand cycle of stellar life. A massive star dies and explodes. Its remnants mix into a nebula, and that disturbance helps give birth to the next generation of stars. Generations of stars are linked across time by these explosions, each supernova enriching the galactic gas with heavier elements and stirring it up. Our own sun and planets were born from such an enriched cloud, one polluted by the ashes of countless ancient supernovae. In a very literal sense, the death of those stars made possible the birth of our solar system. The cycle of stellar life and death is evident in places like the Pillars of Creation or the Orion Nebula, where young stars shine amidst clouds seeded with heavy elements, likely kicked into motion by long-ago supernova blasts. Even now, across the Milky Way, supernova shockwaves are slamming into clouds, sculpting them, sometimes triggering new stars, sometimes dispersing the gas and halting star formation in that region. Supernovae are the galaxy's great architects and janitors. They shape the environment, sweeping clean some areas, clumping material in others. They regulate the very ecology of the galaxy, ensuring that star formation does not proceed too fast or too sluggishly. Without the energy injection from supernovae, gas might collapse into stars more efficiently, exhausting galactic gas early, or conversely, without supernova-induced compression, some stars that exist today might never have formed at all. In these ways, the violence of supernovae helps maintain a balance, distributing gas and heavy elements widely and preventing any one part of a galaxy from hogging all the raw material for starbirth. After the brilliant light of a supernova fades, what remains? Often, at the center of the expanding debris, there lies a newborn neutron star, the collapsed core of the star, now an ultra-dense sphere, perhaps only a dozen kilometers across. It may be spinning rapidly and emitting beams of radiation as a pulsar. In other cases, if the original star was hefty enough, Nothing macroscopic remains at the core. The remnant core collapses all the way to a black hole, an abyss from which not even light can escape. Surrounding that central remnant, we see the supernova remnant, an expanding cloud of gas that was once the star's outer layers. The Crab Nebula is one such remnant, the tattered filamentary remains of a star that blew itself apart in the year 1054 AD. In the Crab's center, a pulsar spins, energizing the nebula with winds of particles. Over thousands of years, these remnants, like the Crab or Cassiopeia A or SN 1987A's debris, will disperse into the general interstellar medium, blending their enriched guts into the galaxy's gas. Astronomers glean a wealth of information by studying the light from supernovae and their remnants. Each element in the ejected gas produces specific spectral lines, bright or dark lines at particular colors, that act like fingerprints. By splitting the supernova's light through a spectroscope, scientists can identify which elements are present in the explosion's debris. For example, they might see lines of hydrogen, or of silicon, or oxygen, or calcium. These tell us the composition of the star's layers and the products of its nuclear burning. A supernova's spectrum changes over time as the explosion evolves. Initially, it may show signs of the hot, dense conditions. Then, as the ejector expands and cools, distinct element signatures emerge. Type Ia supernovae, for instance, are notable for a strong silicon line in their early spectrum, betraying their white dwarf origin. Type II supernovae often show hydrogen lines from their outer envelopes and later a rich soup of lines from metals synthesized in the blast. By analyzing these spectral fingerprints, we confirm that the building blocks of planets and life are synthesized in these explosions. We see freshly minted nickel decaying into iron. We see radioactive cobalt. We see oxygen, magnesium, sulfur, and more, all mixed in the stellar debris. Each supernova is like an autopsy of a star, the spectral lines revealing the star's inner secrets and the outcome of its final nuclear reactions. Beyond visible light, supernovae emit across the electromagnetic spectrum. In fact, some of the most telling signs of a supernova come in forms of light our eyes cannot see. X-rays, for example, are emitted by the supernova shock, heating the surrounding gas to tens of millions of degrees. Observatories like NASA's Chandra X-ray telescope have captured the X-ray glow of supernova remnants, revealing elements via their X-ray spectral lines and showing how the shockwave propagates. Radio waves, on the other hand, arise from electrons accelerated to near light speed by the magnetic turbulence in the shock front, a process known as synchrotron radiation. Many supernova remnants, like the famous Cassiopeia A, shine brightly in radio, appearing as expanding rings or shells. By tuning into radio, astronomers map the size and expansion speed of the remnant, and even discern clumpy structures in the ejector. Infrared observations peer through dust that visible light cannot penetrate, allowing us to see newly formed dust within supernova remnants, or the light echoes reflecting from interstellar dust. Across the spectrum from gamma rays to radio, the supernova broadcasts its story. Gamma ray telescopes detect the high-energy photons from the decay of radioactive elements like nickel, 56, and cobalt, 56, forged in the explosion, direct evidence of the nuclear synthesis that occurred. In 1987, when a supernova exploded in a nearby dwarf galaxy, detectors on Earth even caught a flurry of neutrinos, those ghostly particles arriving hours before the visible light, a stunning confirmation of core collapse theory. That was the first time humans directly detected neutrinos from a supernova, proving that in those dark, silent moments deep inside the star, a huge neutrino release truly occurred. Today, neutrino observatories lie in wait for the next nearby supernova. An international network of underground detectors forms a kind of early warning system. If multiple detectors suddenly register a burst of neutrinos, astronomers know that somewhere in our galaxy, a star's core has collapsed.
They will scramble to point telescopes and catch the light from the explosion as it emerges. In this way, even the nearly undetectable neutrinos serve as messengers, giving us a heads up that a star has died before we even see the flash. We have also developed all sky surveys to catch the optical flash of supernovae as early as possible. Robotic telescopes scan the heavens nightly, comparing new images to older ones, looking for the sudden appearance of a new point of light. Projects like the Young Transient Surveys have netted hundreds of supernovae, some captured just hours after explosion. With each new discovery, alerts go out across the globe so that larger telescopes can begin detailed observations immediately. The goal is to witness the opening act of a supernova, something historically rare. For most of human history, we only saw supernovae days or weeks after they ignited, when they were bright enough to notice by eye. Now, sensitive instruments can catch the very moment a supernova goes off, capturing the initial flash of the shock breaking out of the star. These early moments contain unique information. For example, a brief pulse of ultraviolet or X-ray light may reveal the radius of the star. By catching supernovae early, we peel back the curtain on the star's final preparations for death. In fact, astronomers have even managed to observe a few massive stars in the final days and weeks before they exploded, a dramatic achievement once thought nearly impossible. In one recent case, a red supergiant star was observed to brighten and shed material a couple of months before it ultimately went supernova. The star was under watch by a telescope in Hawaii during the summer of 2020. It showed unusual turbulence and became enshrouded in a cloud of gas. Then, in September of that year, it exploded as supernova SN 2020 Tetlef. And for the first time, humanity had seen the death throes of a normal massive star prior to explosion. This breakthrough observation suggests that some massive stars undergo a brief period of instability just before core collapse, perhaps ejecting some of their outer layers or experiencing a burst of nuclear burning that causes them to vomit out gas and dust. It's as if the star knew its end was coming and convulsed in its final moments. These pre-supernova outbursts might be more common than we realized, and now that we know what to look for, dedicated monitoring of known massive stars may one day catch another in the act of readying for detonation. Seeing a star alive one week and gone the next brings home the reality that these cosmic giants are not eternal. They live and die on timescales we can witness if we pay close enough attention. Even without these advance warnings, there is no doubt when a supernova has occurred. After the flash, the sky is left with a new glowing remnant that wasn't there before. Ancient peoples who saw guest stars had no way of knowing what they were. We, armed with physics, can decode the event. We might turn our telescopes to the coordinates of a new supernova and quickly pick up the signatures of certain elements, telling us if it was a massive star collapse or a white dwarf detonation. If we see hydrogen lines, we know a massive star kept its envelope, a Type II supernova from a red supergiant. If instead we see no hydrogen, but strong silicon and iron, we know a white dwarf blew itself apart. If we see helium but no hydrogen, that suggests a star that lost its hydrogen shell. No hydrogen or helium, but oxygen, neon, magnesium. That could be a Type Ike, a star that lost even more before exploding. Each kind of star death leaves a distinct fingerprint in the light. With modern instruments, deciphering these fingerprints has become almost routine, turning up stories of stars in their last phases. Some were red supergiants shedding mass, others were Wolf, Rayet stars that left no trace of hydrogen in their supernova, and some, as mentioned, were white dwarfs pushed over the edge by a companion. Among the cosmic blasts we've recorded, there are some especially rare and powerful outbursts. Not all supernovae are equal. A few are exceptionally luminous, far beyond the norm. These are fittingly called superluminous supernova.
Imagine a supernova 10 or even 100 times brighter than a typical core, collapse, or type Ia explosion. Such brilliance strains the known mechanisms. A normal collapse or detonation doesn't easily explain it. Astronomers suspect that in some of these cases, an additional power source is at work. One leading idea is the presence of a newly formed magnetar, a neutron star with an extremely strong magnetic field, pumping energy into the ejector. If a neutron star is born spinning extremely rapidly with a magnetic field thousands of times stronger than a typical pulsar, it can act like a dynamo. As it spins down, it transfers its rotational energy to the explosion, heating the debris and making it glow far more brightly for an extended period. Essentially, the magnetar's energy injection is like a central engine boosting the supernova's luminosity. Another possibility for superluminous events is the collision of the ejector with a dense shell of gas around the star. If the star shed a large amount of mass shortly before exploding, then when the supernova blast hits this material, it converts kinetic energy into light very efficiently, producing an extremely bright display. Some of the most luminous supernovae ever seen might be explained this way. The supernova slams into a cocoon of gas dumped by the star in the years prior, lighting it up. Yet another mechanism, applying to the most massive of stars, is the pair instability supernova, a peculiar fate where a single star so massive basically obliterates itself entirely. In those monstrous stars, the core becomes hot enough that gamma rays start converting into electron-positron pairs, suddenly reducing the radiation pressure and causing the core to contract and ignite an extremely violent thermonuclear burning that tears the star apart completely. Pair instability supernovae are theorized to be the most energetic explosions a star can undergo, even bigger than normal core collapse events. And they leave no remnant at all, just a huge cloud of newly minted heavy elements. Observations of an extraordinarily bright supernova in 2006 suggest it might have been one of these events. That star may have been on the order of 200 solar masses and literally blew itself to bits, producing an incredible brightness sustained by the decay of a large mass of radioactive nickel in its ejector. One superluminous supernova discovered in 2015 and named ASASN Illich astonished scientists by reaching a peak brightness 20 times greater than the combined light of the Milky Way's 100 billion stars. For a time, that one exploding star radiated as much energy as 570 billion suns, the brightest explosion ever reliably observed. To explain such an extreme, researchers proposed that a fast spinning magnetar might be behind it, dumping its rotational energy into the ejector and essentially supercharging the explosion. If true, that magnetar would have to be near the upper limits of what physics allows, a neutron star engine pushing the explosion to luminosities at the theoretical fringe. These rare supernovae stretch our understanding of physics. They are nature's overachievers, forcing us to consider exotic ideas like pair, instability, and magnetar engines to account for their brilliance. But they reaffirm an underlying theme. Even in death, stars can be wildly diverse in how they go. The diversity doesn't end there. Some collapsing massive stars unleash not just light, but also focused beams of energy that we observe as gamma ray bursts. Long duration gamma ray bursts, bursts of high energy gamma photons lasting a few seconds to minutes, have been linked to the deaths of very massive, rapidly rotating stars. In these cases, as the star's core collapses into a black hole, it can form a swirling disk of accreting material around the black hole. Magnetic forces in that disk can launch narrow jets of plasma at nearly the speed of light, boring through the collapsing star and punching out into space. These jets, when they finally escape the star, produce an intense flash of gamma rays, the gamma ray burst. For an observer located along the line of one of those jets,
The collapsing star appears as one of the most violent events in the universe, second only perhaps to the Big Bang itself in instantaneous brilliance.
Gamma-ray bursts are so luminous that we can detect them across the observable universe. They announce the birth of a black hole in the heart of an exploding star, and usually, a supernova is observed in the aftermath.
These events are colloquially called hypernovae by some, essentially a supernova with a GRB, indicating an exceptionally energetic explosion with jets. Not every supernova from a massive star does this. It likely requires special conditions. But when it happens, it's the ultimate cosmic drama. A star not only blows up, but also shoots out a pair of killer beams that can fry anything in their path for dozens of light years. Fortunately, such GRB-oriented supernovae are rare and usually far from Earth. They serve to remind us that the outcome of a star's death can be multifaceted: explosion, collapse, neutron star, or black hole, and sometimes relativistic jets that carry away a huge fraction of the energy. Even within the more mundane kinds of supernovae, nuances abound. Consider the red supergiant stars. When one of these blows up as a Type 2 P supernova, it typically shows a characteristic plateau in its light curve, a period of about 100 days where the brightness remains nearly constant. This plateau is caused by the enormous hydrogen envelope that the star had. The shock heats the hydrogen, and as that extended envelope recombines from ionized to neutral, it releases a steady glow of light over weeks. On the other hand, a blue supergiant progenitor can yield a supernova with a faster rise and decline, since it lacks such a distended envelope of hydrogen. A famous example of this was the supernova observed in 1987. Its progenitor was a blue supergiant, and the light curve was quite different from a standard Type 2P, showing an initial burst and then a dip before rising again. This taught astronomers that not all massive stars explode from the red supergiant stage. Some may explode earlier in their evolution. Meanwhile, some massive stars lose most or all of their hydrogen before exploding. Such stars, often Wolf-Rayet stars, give rise to Type Ib or Type Ith supernovae. These explosions lack the signature hydrogen plateau, since the star's outer layers were gone. Instead, their light curves often decline more quickly and are powered largely by the radioactive decay of nickel, D6 to cobalt, 56 to iron, D6 in the ejector. By studying these differences, astronomers piece together the life histories of the progenitor stars. A Type Ice supernova with broad spectral lines might indicate an especially massive star that was stripped and possibly involved in a binary merger or had extremely powerful stellar winds. A Type 2 with a very long plateau might imply an especially extended red supergiant. Each dying star carries the imprint of its life into its death, visible in the explosion's properties. While we have focused on the dramatic, successful explosions, nature sometimes chooses a more silent finale. In recent years, evidence has emerged that some massive stars fail to go supernova at all, at least not in any luminous way. Instead, they collapse directly into a black hole, disappearing from view with barely a fuss. How would we notice such an event? Imagine a star that brightens a bit, perhaps as its outer layers respond to the initial core collapse, and then fades to nothing, no ensuing explosion. This appears to have been observed in a galaxy about 22 million light-years away, where a star of around 25 solar masses brightened modestly and then vanished, leaving no supernova. It seems that the star's core collapsed, but the shock did not blow the star apart. Instead, nearly the entire star just fell inward, swallowing itself into a new black hole. This phenomenon has been dubbed a failed supernova. It's essentially a collapse without an explosion. Gravity wins completely, and almost all of the star's mass slides past the event horizon of the nascent black hole. Only a feeble burp of energy might escape to tell the tale.
For the galaxy at large, the star just quietly winks out. For the star itself, of course, it is a tremendous end. 98% of its mass collapsing into the black hole, maybe 2% getting flung out in that brief flare as the rest slurps away. Failed supernovae are a stark reminder that not all stellar deaths are flamboyant. Sometimes the star falls silent, leaving a dark remnant with no fireworks. These events are harder to find, but ongoing monitoring projects are trying to identify more of them by looking for massive stars present in old images that have since disappeared without a trace. If higher, mass red supergiants tend to die this way, it could explain why we don't see supernova progenitors above a certain mass. They might simply collapse directly and give no bright supernova, solving a little mystery about the apparent upper mass limit of supernova progenitors. Whether a star dies with a spectacular bang or a quiet collapse, the end result is a compact object and an ejection of material. These remnants then influence their surroundings for a long time. A young pulsar left from a supernova spins inside its nebula, energizing it with winds and radiation. A newborn black hole might produce relativistic jets, or it might just quietly accrete any remaining back material from the collapse. The ejecta from a successful supernova expand and eventually mix into the galaxy's gas. Multiple supernovae in a star, forming region, such as those in a cluster of massive stars, can create superbubbles, huge cavities in the interstellar medium, swept clear by consecutive blasts. In starburst galaxies, where many massive stars die in a relatively short span, the combined effect of many supernovae can drive galactic winds. Enormous outflows of hot gas blowing out of the galaxy's disk into intergalactic space. These winds carry metals out of the galaxy, dispersing the products of star formation far and wide. Thus, supernovae not only shape where new stars form locally, but also how galaxies evolve globally by regulating gas flows. It's thought that without supernova-driven winds, galaxies might contain much more gas and form stars too efficiently early on, whereas with winds, some gas is ejected and star formation is extended over billions of years. Our own Milky Way has fountains of gas likely powered by past supernovae clustered in regions like the galactic center. We even detect cosmic rays, high-speed particles, that originate from the shock waves of long-ago supernovae, still diffusing through space and occasionally hitting Earth's atmosphere. These cosmic rays are a byproduct of supernova remnants. As their shocks propagate, they act like giant accelerators. Particles bounce back and forth across the shock front, gaining energy with each crossing, until some are flung out at near light speed. The Milky Way is filled with these relativistic particles, and about 90% of the cosmic rays that strike us are protons, thought to be accelerated by supernova shockwaves. Supernovae, then, are also cosmic ray factories, shooting out subatomic bullets that zip through the galaxy. Some of those particles may even have affected Earth's biology over the eons by contributing to background radiation or seeding cloud formation. In any case, they are yet another thread of connection between stellar deaths and our own world. On Earth, we have literally found the fingerprints of nearby supernovae in geological records. Deep sea deposits and lunar soil samples contain trace amounts of rare isotopes like iron, Sc, that are not produced in significant quantities by typical earthly processes. The most plausible source is a supernova that occurred a few million years ago near our solar system, dusting us with a thin coat of radioactive ash. Indeed, layers of extraterrestrial iron sounded have been detected in ocean crusts, corresponding to around 2003 million years ago, and even in Antarctic snow from recent times. This is tangible evidence that a supernova occurred in our cosmic neighborhood in the relatively recent geological past. Fortunately, it was not so near as to cause a mass extinction, but near enough to sprinkle Earth with a detectable layer of star stuff. Perhaps such events even had subtle effects on our planet. Some have speculated about minor climate impacts or changes in cosmic ray flux affecting cloud cover. In any case, its
inspiring to realize that Earth has been showered by the debris of explosions that happened far away. We walk amid atoms that fell from the skies of long-gone stars. The very iron in your blood could include atoms flung out by a supernova that occurred before humans walked the Earth. Across cultures and centuries, humans who witnessed supernovae have been mesmerized and mystified. The sudden appearance of a new star, where none had been seen, often regarded as an omen or a divine signal. Ancient Chinese astronomers meticulously recorded these guest stars and noted their brightness and duration. In 1006 AD, a supernova in our galaxy was recorded as a star bright enough to read by at night. In 1054, the supernova that created the Crab Nebula was observed by Chinese, Japanese, and possibly Native American skywatchers, who saw a star rivaling the moon's brightness for weeks. In Europe, the notion of an unchanging heaven was challenged in 1572, when Tycho Brahe observed a brilliant new star. It helped upend old models of the cosmos. These events entered law and record. They were variously interpreted as heralds of great change, the births of new celestial beings, or the wrath of gods. One can imagine ancient peoples gazing up in wonder and fear at a glowing orb that hadn't been there before, not knowing they were witnessing the death of a distant sun. They lacked our scientific understanding, but they felt the grandeur of the event. They called them new stars, not realizing they were actually witnessing a star's death, or more poetically, its transfiguration. In a way, the ancients were right to be awed. These guest stars were harbingers, though not of human affairs, but of cosmic renewal. They heralded the dispersal of elements that would one day form new stars, new planets, perhaps new living beings. Today, with knowledge in hand, our awe has only deepened. We no longer see supernovae as unpredictable omens. We see them as essential processes in the universe. They are the engines of cosmic evolution, the means by which simple matter is churned into complexity and spread throughout galaxies. They are at once destructive, obliterating a star, potentially sterilizing nearby planets, and creative, sowing the seeds of creation far and wide. In their violence, there is profound generosity. The star gives all it has to the cosmos in its final moment. The gas and dust rushing outwards will, in time, collect into new clouds, igniting new stars with planets around them. Perhaps on those planets, new life will one day spring forth, built from the atoms of that long, dead star. This cycle links us to the stars in an intimate way. Look at the gold of a ring on your finger. Those gold atoms likely formed in either a supernova or a neutron star merger eons ago. The calcium in your teeth was flung out by an exploding star before the sun was born. When you gaze at the night sky, you are literally seeing ancestors of your own flesh and blood. Philosophers and poets have long noted the connection between death and rebirth. In mythology, the phoenix is a creature that bursts into flame, and from its ashes, a new phoenix rises. The universe offers its own phoenix tale. A star dies in fire, and from its ashes, new stars arise. Every supernova is a phoenix event on a grand scale. The ashes do not remain cold and dead. They eventually become the building blocks for new astral flames. The cosmic dust from supernovae drifts through space for ages, but given the tug of gravity and the shelter of a molecular cloud, it can coalesce again. Our solar system is one such recoalescence, a mix of gas and supernova dust that assembled into a star, planets, and on one of those planets, creatures who can ponder the process. It is a humbling and inspiring realization. The universe recycles. Stars sacrifice themselves so that the cosmos can be ever more enriched and complex. In a poetic sense, the stars die so that we might live. As we conclude this journey through the death of stars, we stand in awe of the grand narrative it presents. A supernova is not an isolated incident. It is a chapter in the cosmic story. It's the dramatic climax in the life of a massive star, but also the prologue for the matter that star releases. From the soundless flash that announces a star's demise to the glittering nebula that remains and the new stars that will be born from it, the supernova story is a saga of transformation. It reminds us that even in destruction, there is profound creativity. The universe takes the incandescent bow of a star and uses it to sow gardens of new suns. The next time you look up at the night sky, consider that somewhere out there, at this very moment, a star is meeting its spectacular end. You will not hear it, but if the star is close enough and your timing fortunate, you might one night see a new point of light. A silent shout across space, the death cry of a star that lived perhaps millions of years. And though it died alone in the vacuum, its effects will not be lonely. The elements it scatters will mingle and dance in nebulae. Some will become parts of new living beings who may one day also look up and wonder. In the grand scheme, the death of stars is as necessary as their birth. From cosmology's perspective, stars must die for galaxies to thrive and for life to exist. Our world is the way it is because countless stars died in the Milky Way before the sun even ignited. There is an emotional power to this knowledge. We see in the supernova a reflection of a natural truth, that endings feed beginnings, that great beauty can arise from great upheaval. The supernova is violent, yes, a masterpiece of cosmic violence, but it is also the universe's most brilliant creative act, forging heavy atoms and casting them forth to enable planets and life. It is the universe writing poetry with fire, a verse about impermanence, transformation, and interconnection. The star which lived in solitude ends by giving itself to everything. Its light races across the cosmos. Its shrapnel becomes the stuff of new worlds. In contemplating the death of stars, a supernova story, we find ourselves filled not with despair, but with a profound sense of connection and renewal. The atoms in our bodies were born in stellar furnaces and scattered by supernova, binding us to those majestic events. When we marvel at a supernova through a telescope, we are in a way beholding our own origins. The cosmos is not a static, cold place. It is dynamic and alive. Stars living and dying in an endless cycle, enriching the darkness with each burst of light. So the next time a star dies in our galactic neighborhood and graces our night sky as a brilliant guest star, let us step outside in the quiet night and look up. Let us remember that we are witnessing the end of a long story and the beginning of countless new ones. In that radiant bloom of stardust is the promise that life goes on, that from cosmic death comes cosmic rebirth. It is a sight at once heartbreaking and heartening, the universe transforming itself, the phoenix rising anew from the ashes of a star. We are privileged to behold it, and even more, to be it, for we are made of that very stardust. In the death of stars, we find not only the grandeur of nature's fiercest power, but also our own heritage written in light. The tale of the supernova is the tale of us all. In the silent depths of space, a star is dying. After millions of years of shining, pouring light and warmth into its corner of the galaxy, the star's final moment has arrived. It happens in an instant. The star's core collapses, and then, boom! A titanic explosion tears the star apart from within. Brilliant light floods the darkness. For a few blinding weeks, this single dying star outshines the billions of other stars in its galaxy. Its outer layers are hurled into the void, carrying a treasure of newly forged elements. In the aftermath, a glowing cloud of stellar debris, rich with hues of neon blues and fiery reds, laced with specks of gold, expands outward, and at its center, a strange new object is born from the star's crushed heart. This is a supernova, the spectacular death of a star. It is both an ending and a beginning,
a cosmic death and rebirth wrapped into one event. Supernovae are the universe's great paradox. They are violent, destructive events, the most powerful explosions since the Big Bang. Yet from their chaos comes creation. When a massive star dies in a supernova, it doesn't vanish without a legacy. The brilliant blast is a final act that seeds the cosmos with matter that will become new stars, new planets, perhaps even new life. In a very literal sense, our own existence is connected to these explosions in the sky. Every atom of calcium in our bones, of iron in our blood, of oxygen that we breathe, was forged in the cores of stars and cast across space by supernova explosions. The universe recycles itself through these stellar deaths. In the ashes of dead stars lie the ingredients of future worlds. To understand how such an immense explosion happens, we must first understand the life of a star. Like living creatures, stars have life cycles. They are born, they age, and they die. A star's fate, the way it dies and what it leaves behind, depends on its mass, the amount of matter it contains. Small stars live long, steady lives and perish quietly. Very large stars live short, furious lives and die in cataclysmic blasts. Imagine a stellar nursery, a cold, dark cloud of gas and dust in space. Over time, gravity draws parts of this cloud together into clumps. One clump grows denser and hotter at its core until a new star ignites, shining with nuclear fire. This infant star spends most of its life steadily fusing hydrogen into helium in its core, a process that releases the light and heat we see from stars. For a star of modest size, like our Sun, this phase lasts billions of years. Eventually, the star depletes the hydrogen at its center. No longer able to produce the same energy, the core begins to contract under gravity. The star's internal furnace seeks new fuel. It raises the core temperature until helium, the ash of the previous stage, can fuse into carbon and oxygen. The star's outer layers swell enormously and cool as this happens, and the star becomes a red giant, hundreds of times larger than before. Our Sun will follow this gentle path. About 5 billion years from now, it will expand into a red giant, likely swallowing Mercury and Venus and turning Earth into a scorched ember. The Sun's light will turn bloody red, and its size will loom vast in the sky. But the Sun is not destined to explode as a supernova. It simply isn't massive enough. After it has fused helium into carbon and oxygen, it will shed its outer layers into space, creating a glowing planetary nebula, a shell of colorful gas expanding away into the darkness. Ultimately, the Sun's core will be left behind as a small, hot, white dwarf about the size of Earth. It will glow faintly with residual heat for billions of years, slowly cooling and dimming. That will be the Sun's quiet end, a final cosmic whisper rather than a shout. But for stars significantly more massive than the Sun, the story plays out quite differently. A star, perhaps 10 or 20 times the Sun's mass, lives fast and dies young. These massive stars burn through their nuclear fuel at a prodigious rate. Live fast, die young could describe them. They shine tens of thousands or even hundreds of thousands of times brighter than the Sun, but exhaust their core fuel in only a few million years. As a massive star ages, it undergoes a vivid transformation. After burning through its core hydrogen, it becomes a red supergiant, much like the famous star Betelgeuse in Orion's shoulder, a colossal swollen star so large that if it replaced our Sun, its surface might extend beyond the orbit of Mars. Inside its core, the star is a raging furnace, fusing heavier and heavier elements in successive stages. Hydrogen fuses to helium, helium fuses to carbon and oxygen, carbon fuses into neon, sodium and magnesium, neon burns to oxygen and magnesium, oxygen fuses into silicon and sulfur, and, finally, silicon fuses into iron and nickel. In the star's final days, its interior resembles a giant onion with layered shells of different elements. each shell the burning ash of the previous fuel, nested one inside another. Then the star reaches a fatal threshold: iron. When iron accumulates in the core, the star has run out of road. Fusing iron doesn't release energy, it consumes energy. The mighty engine at the star's center, which for millions of years has fought against gravity by pumping out heat and pressure, suddenly falters. With no new energy to support it, the iron core is overwhelmed by the star's immense weight. In a fraction of a second, the core implodes. The inner core, once perhaps the size of Earth, collapses to something only a dozen kilometers across. At the immense densities achieved, protons and electrons in the core smash together and merge into neutrons. The core, now essentially a ball of neutrons, is as dense as an atomic nucleus. The collapse is so violent that temperatures spike to billions of degrees. A flood of neutrinos, ghost-like subatomic particles, pours out of the core, carrying away a tremendous amount of energy. For a moment, it seems as if the entire star might simply disappear into itself. But when the core's collapse is finally halted, something extraordinary happens. The imploding core bounces outward, sending a shockwave racing back up through the infalling layers of the star. Those trillions of neutrinos streaming out also deposit energy into the surrounding matter. Within milliseconds, the rebounding shockwave is energized and blasts outward through the star's layers. The star's outer regions, which have been rushing inward, now are violently blown outward at incredible speeds. The energy released is staggeringly large, comparable to the total energy the Sun will radiate over its entire 10 billion-year lifetime, unleashed in a single burst lasting only a few seconds. The star has become a supernova. If you could stand on a hypothetical planet orbiting such a star, the experience would defy imagination. In the days leading up to the explosion, you might see your sun swelling into a red giant, its color deepening to a dusky crimson, its light fading and flickering as it sheds its outer layers. The sky might glow strangely as the star ejects shells of gas. Then, seemingly without warning, the end comes. One moment, the night side of your planet is dark and serene, the bloated red sun hanging low on the horizon. The next moment, a blinding flash ignites the sky, as if 1,000 full moons have risen at once. The star erupts with ferocity unimaginable, outshining entire constellations. In seconds, a wave of intense radiation scorches the planet's surface. The atmosphere itself might ignite in a brief, furious glow. Within minutes, the crushing blast front arrives, a wall of plasma and gas moving at millions of kilometers per hour. If the planet is close enough, it would be stripped of its atmosphere and perhaps shattered entirely. It is a celestial cataclysm beyond comprehension. Thankfully, we observe supernovae from the safety of tens of thousands of light years away, where their violence translates only into a wondrous light show in the sky and a rain of subatomic particles that pass harmlessly through us. From hundreds or thousands of light years away, a supernova appears as a sudden new star that wasn't there before, often outshining all the normal stars around it. It can start as an unremarkable pinprick one night, and then, night after night, grow in brightness until it rivals the brightest stars or even the moon in the sky. For weeks, sometimes months, it remains brilliant, visible even in daylight if it's close enough, and then gradually it fades, shrinking back into the darkness as its energy is expended. Eventually, it disappears from casual view entirely, leaving behind only the expanding cloud of debris visible to telescopes and, at the center, a strange new stellar remnant marking the place where the star's heart was. Not all supernovae, however, come from the core collapse of a massive star. There is another pathway to these cosmic explosions, one that involves a kind of star that has already died once. When a star like the Sun dies, as we said, it leaves behind a dense core called a white dwarf. A white dwarf is extremely dense. Imagine packing the sun's mass into a sphere the size of the Earth, and it's made mostly of carbon and oxygen, the ash of the sun's core fusion. Normally, a white dwarf simply cools and fades over eternity, but in a close binary star system, a white dwarf can get a second chance at a dramatic exit. If the white dwarf orbits a companion star, the white dwarf's intense gravity may begin stealing gas from its partner, siphoning matter onto itself. Over time, the white dwarf grows heavier. As it gains mass, it grows more and more compressed, and its core temperature climbs. If the white dwarf approaches about 1.4 times the mass of our Sun, the pressure and temperature at its center becomes so high that carbon fusion ignites explosively throughout the star all at once. The white dwarf, in effect, becomes a gigantic nuclear bomb. In a fraction of a second, a thermonuclear chain reaction races through the dwarf star's carbon and oxygen interior, unleashing an atomic inferno that blasts the white dwarf to bits. The star is completely destroyed in a furious thermonuclear supernova. In some cases, two white dwarfs in a binary system can also spiral into each other and merge, likewise igniting a catastrophic supernova without needing gas from a normal star. Different route, same destination, an explosion. Astronomers classify supernovae based on the light they emit, especially the fingerprints of elements seen in their spectrum. The first big distinction is simple. Does the supernova's spectrum show hydrogen or not? Hydrogen, the most common element, usually makes up the outer layers of stars. A supernova that clearly shows hydrogen in its ejected material is called a Type II supernova. These are typically the core collapse explosions of massive stars that retain their hydrogen envelopes right up to the moment of death. Other supernovae show little or no hydrogen in their spectra. These are generally called Type I. The white dwarf explosions in binary systems are one subtype of Type I, specifically Type Ia supernovae. They have a distinctive spectral signature. No hydrogen lines at all, but a strong absorption line of ionized silicon, plus later an emergence of ion lines. These indicate the presence of elements like silicon and iron synthesized in the explosion. Type Ia supernovae, being born of similar white dwarf trigger conditions, also reach almost the same peak brightness, which made them incredibly useful, as we'll see later. There are also types Ib and Ike, which, like Type II, are core, collapse explosions of massive stars. But in these cases, the star had lost its outer hydrogen layers before it exploded. Such stars might shed their outer layers through powerful stellar winds, or by transferring mass to a companion star earlier in their life. So, when they finally explode, little or no hydrogen is left to appear in the spectrum. Type Eb supernovae show helium lines, and Type Ike show neither hydrogen nor helium clearly. Despite these differences in label, the fundamental mechanics are similar. The star's core collapses and blows the star apart. Astronomers can tell the types apart by looking at the supernova's spectrum. For example, a Type Ia will have a telltale line of singly ionized silicon at about 615 mm wavelength near maximum light, while a Type II will show hydrogen Balmer lines. These subtle fingerprints in the light are the clues that let us decode what kind of star died and how. So, whether it's a massive star's core collapse or a white dwarf's detonation, the result is one of the most powerful blasts in the universe. The energy and light released are so great that for a short time, a single supernova can outshine an entire galaxy of normal stars. It's as if 1 billion suns all went off in one location. No wonder early sky watchers were astonished by them. Throughout human history, supernovae in our own galaxy have occasionally announced themselves to human eyes, becoming brilliant beacons in the night. Long before modern science, people looked up and saw these new stars appear where nothing had been visible before, and they were awestruck. The records of these events are etched in history. In the year 1054 AD, Chinese astronomers noted a dazzling guest star in the constellation we now call Taurus. It shone so brightly that, according to their records, it was visible in the daytime sky for weeks and at night for nearly 2 years. We can imagine an imperial astronomer in 1054, waking before dawn, climbing to his observation platform on the city wall, and rubbing his eyes in disbelief at a brilliant new star near the red hue of Aldebaran. This guest star, as they called it, would have been an object of both scientific curiosity and perhaps portent. Dutifully, he records its position and brightness on a scroll for the emperor's archive, perhaps wondering what heavenly omen this might signify. Chinese court astronomers were meticulous. Night after night, they tracked the guest star's dwindling brightness until it faded from sight nearly 2 years later. That guest star of 1054 eventually faded from human view, but it left a permanent mark on the sky. Today, modern telescopes reveal at its location the Crab Nebula, a sprawling, tangled cloud of gas and dust, expanding outward. Those filaments and tendrils are the remains of the star that exploded, still racing outward at thousands of kilometers per second. And at the heart of the Crab Nebula lies a tiny, incredibly dense neutron star, the pulsar we mentioned, rotating about 30 times a second. It is the leftover core of the star that blew itself apart in 1054. Of course, the astronomers of the Song dynasty could not have known about neutron stars or nebulae, but they knew the event was extraordinary. Their careful documentation allows us, centuries later, to connect the Crab Nebula to the 1054 supernova. Another great supernova lit up Earth's skies in April of 10,006 AD. By all accounts, it was likely the brightest stellar event ever recorded by humans. Observers from East Asia to the Middle East and Europe noted its appearance. In China, records say it was as bright as the planet Venus, and in some places it was even visible in daylight. In Japan, chronicles describe it as a dazzling guest star. In the Middle East, the Egyptian Arab astronomer Ali ibn Ridwan wrote that the spectacle in 1006 was a third the brightness of the moon and cast shadows on the ground at night. Imagine that, walking at night by the light of an exploding star. People didn't know what to make of it. Some thought it a mighty omen, others simply a marvel. We now identify this event as SN 1006, and its faint glowing remnant has been found about 7,200 light years away, near the constellation Lupus. Evidence suggests SN 1006 was likely a Type Ia supernova, a white dwarf explosion, given the lack of a neutron star remnant and the composition of the debris. It's humbling to realize that what was probably the obliteration of a small dead star could produce a light visible across an entire hemisphere of Earth. In 1572, a supernova appeared in the constellation Cassiopeia, and it profoundly affected the course of astronomy. The Danish nobleman Tycho Brahe, one of the most meticulous sky observers of his era, was astonished to see a brilliant new star where no star had been before. It outshone even Venus. Tycho later wrote that no poet could ever capture how beautiful and bright this new star was. He called it Nova Stella, the new star. Tycho diligently measured its position night after night against the background of fixed stars, and found, critically, that it exhibited no parallax, meaning it was not a nearby object in our atmosphere, but far beyond the moon, among the stars. This was a direct challenge to the prevailing Aristotelian belief that the heavens were immutable and unchanging. If a star could suddenly appear, the heavens were not eternal and perfect after all. Tycho published his observations in a famous work, De Stella Nova. His discovery sparked widespread discussion in scholarly circles across Europe. Today, we call this event Tycho's supernova. More than 4 centuries later, modern telescopes have captured an expanding bubble of debris at the spot in Cassiopeia where Tycho's star was, an object now known as Tycho's supernova remnant. It's an almost spherical shell of gas, glowing in X-rays. From its characteristics, we infer that Tycho's supernova was likely a type Ia supernova as well. Tycho had witnessed the self-destruction of a white dwarf star from 10,000 light-years away, without knowing it. What he did know is encapsulated in his own words. "I have watched a new star, not seen before in any age, break out and subsequently disappear." The heavens could change. Only 32 years after Tycho's discovery, in 1604, another brilliant new star appeared, this time in the constellation Ophiuchus. It was observed by many, including astronomer Johannes Kepler in Prague. Kepler studied it carefully and wrote a book about it, De Stella Nova. At its peak, this 1604 supernova was brighter than Jupiter and could even be glimpsed in daylight. It gradually faded over a year and a half. Kepler's findings, like Tycho's, confirmed that the new star had no measurable parallax, placing it far beyond the Moon. In Italy, Galileo Galilei gave public lectures about the 1604 nova, using it as evidence that contradicted the Aristotelian doctrine of an unchanging cosmos. The appearance of these supernovae in 1572 and 1604 within a human lifespan dealt a serious blow to ancient astronomy and helped usher in a new, dynamic view of the universe. Kepler's supernova of 1604 is the last supernova in our Milky Way that has been clearly observed with the naked eye. Little did astronomers of the time know, it would be more than 4 centuries before another such event would be seen in our galaxy. Interestingly, a supernova did occur later in the 17th century, around 1680, but it was not widely observed, or at least not recorded in surviving documents. We know of it only from its ghost, the Cassiopeia, a supernova remnant. This ragged, expanding shell of debris, glowing in radio waves and X-rays, marks the remains of a massive star that exploded roughly 340 years ago. Why was it not noted like Tycho's or Kepler's? Possibly the explosion was obscured by interstellar dust, dimming its visible light before it reached Earth. Recent calculations indicate that the star that became Cas A might have ejected a lot of its mass before exploding, so the supernova's optical light was much fainter than expected. There is a tantalizing historical hint. The English astronomer John Flamsteed in 1680 recorded a faint star in Cassiopeia that was not seen before or after. That could have been the fleeting sight of Cas A's supernova, but we can't be certain. In any case, Cas A's existence, only revealed later by our telescopes, reminds us that not all stellar catastrophes announce themselves obviously. Some are missed by history, hiding in the obscuring folds of the galaxy. After Kepler's 1604 supernova, centuries passed, with no new nova stella blazing forth in our skies. But astronomers continued to watch and to wonder. In 1885, a sudden star, like light, appeared in the Great Andromeda Nebula. At the time, astronomers noted this nova and were puzzled that such a bright outburst could happen in what they thought was just a nebula. Only later did we realize this was a supernova in an entirely separate galaxy, the first ever recorded outside the Milky Way. This was a hint that such explosions occur everywhere, not just in our own cosmic backyard. In the early 20th century, our understanding of supernovae took great leaps. 2 astronomers, Walter Baade and Fritz Zwicky, working in the 1930s, made a bold proposal. They suggested that supernovae were the cataclysmic transition of ordinary stars into neutron stars, extremely dense stellar remnants composed mostly of neutrons. In 1934, barely 2 years after the neutron particle had been discovered in physics experiments, Baade and Zwicky coined the term supernova to distinguish these titanic stellar explosions from the more common, far less powerful novae. They hypothesized that the tremendous energy of a supernova could be explained by the gravitational collapse of a star's core, compressing electrons and protons into neutrons. In their vision, the star's outer layers would be violently ejected and the core would remain as a neutron star. This hypothesis was revolutionary. essentially science fiction to their colleagues at the time. They also speculated that supernovae could be sources of cosmic rays, and that these explosions fundamentally influence galactic ecology. For decades, these ideas remained unproven theory, but bit by bit, evidence accumulated. By the 1940s, astronomer Rudolf Minkowski had studied the spectra of supernovae in other galaxies and noticed the differences that led to the classification into Type 1 and Type 2. That was a clue that there were different causes. In 1964, a young astronomer named Antoni Przybylski even suggested that the Crab Nebula's central star might be a spinning neutron star, though this wasn't confirmed until a bit later. Then, in 1967, the first pulsar was discovered by Jocelyn Bell Burnell. Pulsars were quickly identified as rapidly spinning neutron stars emitting lighthouse-like beams of radiation. In early 1968, scientists recognized that a known pulsar in the Crab Nebula was located exactly where the 1054 supernova had been seen, and its characteristics matched what a neutron star would be. This was the smoking gun that Bard and Zwicky had been right. Supernovae do produce neutron stars. The Crab Nebula pulsar flashes 30 times a second, unmistakably a neutron star left from that explosion. From then on, the picture became clearer. By the late 20th century, astronomers had detected supernovae in countless distant galaxies and understood that when we see a distant galaxy suddenly pinpricked by a new gleam, it's likely a star reaching its grand finale. We finally had a coherent narrative. Massive stars explode as supernovae and leave neutron stars or black holes. White dwarfs explode as supernovae and leave no remnant, but create a wealth of heavy elements. The theoretical bold strokes of Zwicky and Bard had become an observational reality. All this set the stage for one of the most significant supernova observations in modern times, Supernova 1987A. In February 1987, astronomers in the southern hemisphere spotted a new star in the Large Magellanic Cloud, a small companion galaxy to the Milky Way, about 168,000 light-years away. On the night of February 23, 1987, at an observatory in the Chilean Andes, a young astronomer named Ian Shelton was developing a photographic plate he had just exposed of the Large Magellanic Cloud's starfield. To his surprise, on the fresh image, a star glowed in a spot where no star had appeared on older charts. Thinking it might be a flaw in the plate, he stepped outside and gazed toward the faint smear of the LMC with his own eyes. There it was, a bright pinpoint of light in the Tarantula Nebula region that hadn't been there before. In that moment, he realized he was witnessing a star's death cry from across 168,000 light-years. He rushed to announce the discovery. Within hours, news of the new supernova spread worldwide, and telescopes everywhere turned to observe it. The object was named SN 1987A. It was the closest supernova observed since Kepler's of 1604. Though being in another galaxy, it was visible only from the southern hemisphere. Southern hemisphere observers, both amateur and professional, were treated to a faint star that rapidly rose to about magnitude 3, easily visible to the naked eye. SN 1987A turned out to be an unusual supernova in many ways. The star that exploded was identified on old photographs. It was a blue supergiant star, about 20 times the mass of the Sun. This was unexpected, as theory had predicted red supergiants as supernova progenitors. It suggested the star had an interesting evolutionary history. The supernova's brightness peaked and then decayed over months, as expected. But what truly electrified the scientific community was an invisible signal that accompanied the explosion: neutrinos. About 2 hours before the first light from SN 1987A reached Earth, detectors deep underground in Japan, the United States, and the USSR picked up a flurry of neutrinos, nearly 24 in total across the detectors. These ghostly particles had been emitted from the collapsing core of the star, and, unlike photons, they escaped unimpeded and raced out ahead of the light. It was the first time humans detected neutrinos from beyond our solar system, and it was direct evidence of the core collapse mechanism. In fact, Kamiokande 2 in Japan recorded 12 neutrinos, the IMB detector in the US recorded 8, and the Baksan detector in Russia recorded 5, for a total of 25 neutrinos, an almost absurdly small number out of the 10^8 neutrinos the supernova emitted, yet more than enough to confirm theoretical predictions. Those neutrinos arrived around 3 hours before the optical explosion was seen. They provided proof that 99% of the energy of the collapse went into neutrinos, just as theory had suggested. They also gave astronomers about a 3-hour heads up that something spectacular was about to happen in the LMC. The detection of neutrinos from SN 1987A was a milestone. It marked the birth of neutrino astronomy and validated crucial aspects of supernova theory. But even with such breakthroughs, the exact details of how a collapsing star's core launches the supernova shock remain an active area of research to this day. Astrophysicists use some of the world's most powerful supercomputers to simulate core collapse supernova because the physics is extremely complex. It involves hydrodynamics, nuclear physics, neutrino transport, and general relativity all at once. These simulations have largely validated the idea that a flood of neutrinos from the forming neutron star can re-energize the stalled shockwave and cause the star to explode instead of simply imploding. But many subtleties remain. In some simulations, slight differences in how the stellar core convects or how neutrinos oscillate in flight can determine whether the star blows up or collapses quietly into a black hole. Each new observed supernova provides data to refine these models. SN 1987A, for instance, taught us volumes, yet also raised questions. It showed that while we conceptually understand supernovae, we still have mysteries to solve about the precise physics in those last split seconds. After the brilliant flash of 1987A faded, it left behind a changing scene that astronomers have continued to study. The Hubble Space Telescope and other observatories have monitored SN 1987A's remnant over the decades. We saw a beautiful structure of 3 rings around the site of the explosion, material the star had blown off in epochs before it died, now glowing as the supernova's shockwave slams into it. Over time, those rings began to brighten as shock, heated knots of gas lit up, looking like a pearl necklace in space. SN 1987A also confirmed that supernovae create new elements. As its debris cooled, astronomers detected the spectral signature of freshly synthesized radioactive cobalt (SEC), produced from the decay of nickel that was forged in the blast. This matched predictions that a Type II supernova would create about 0.07 solar masses of nickel (SEC). Indeed, SN 1987A made roughly the equivalent of 20,000 Earth masses of iron in one go, along with abundant oxygen, sulfur, and other elements. Talk about cosmic alchemy. Even now, a faint glow persists at the supernova's location, a mix of radioactive embers and shock-heated gas. Astronomers strongly suspect a neutron star was born in SN 1987A, but initially, we couldn't see it due to dense dust in the core. Hints of a hot compact object have emerged in the last few years with improved observations. It's likely hiding, still too shrouded to detect directly. If and when it's confirmed, SN 1987A will have given us the full story. Star to supernova to neutron star, observed almost from start to finish. From ancient skywatchers to modern astronomers, supernovae have evoked awe and curiosity. But beyond their visual drama and historical significance, they play a central role in the cosmic ecosystem. These explosions are key to understanding how the universe manufactures the elements that make up planets and people. This process, creating new atomic nuclei out of lighter ones, is called nucleosynthesis. While steady fusion in stellar cores creates elements up to iron over millions or billions of years, supernovae create the heavier elements in mere seconds.
They are nature's factories for the elements heavier than iron through processes that occur during the explosion. Inside a core, collapse supernova. When the core implodes and then launches the shock outward, conditions become extreme. Temperatures of billions of degrees and densities trillions of times denser than lead cause an avalanche of nuclear reactions. One of the most important is the IR process, the rapid neutron capture process. In the turmoil of the exploding star, atomic nuclei are bombarded by an enormous flux of free neutrons. Nuclei that would normally be stable quickly absorb neutrons and become very heavy unstable isotopes. These then undergo radioactive decays to form stable elements heavier than iron. In mere seconds, elements like silver, tin, iodine, xenon, gold, platinum, uranium, elements that cannot be produced in the normal life of a star, are synthesized in the heart of the explosion. A core, collapse supernova, is like a gigantic atom smasher, forging the heaviest elements on the periodic table. Meanwhile, the shockwave also drives fusion in the outer shells of the star as it plows through them. This shock nucleosynthesis creates large amounts of intermediate weight elements: silicon, sulfur, argon, calcium, and nickel. Type Ia supernovae contribute as well. In the explosion of a white dwarf, essentially the entire star undergoes uncontrolled fusion. Carbon and oxygen fuse into elements like magnesium, neon, and mostly nickel. Type Ia supernovae are prolific producers of iron and nickel in the universe. Those white dwarf bombs are the primary source of the iron, group elements that exist in galaxies. The upshot of all this, supernovae of both types are responsible for most of the elements heavier than helium in the universe. When the universe began, after the Big Bang, it had mostly hydrogen and helium. The rest of the periodic table, from carbon and oxygen to iron, gold, lead, and uranium, would be built later in stars. But many of those elements required the unique conditions of a supernova to form. Every supernova is a chemical foundry, forging elements and then blasting them out into space. A single supernova can manufacture an astounding amount of heavy material. For instance, calculations suggest a typical Type II supernova might create around half the mass of our Sun in heavy elements and eject them. That could include tens of thousands of Earth masses worth of oxygen, iron, and other crucial ingredients. These newly minted atoms are flung into interstellar space, carried on the expanding blast wave. But the story doesn't end with the creation of these elements. It continues with their dispersal and recycling. The glowing, expanding cloud of debris from the supernova, now called a supernova remnant, spreads out into the surrounding interstellar medium. Over years, decades, and centuries, we can track these remnants as they grow. They become beautiful to our telescopes. The Crab Nebula's spiderweb of filaments, illuminated by an inner blue glow from the pulsar wind, or the Veil Nebula in Cygnus, draped across the sky like delicate gossamer ribbons, or Tycho's remnant as an X-ray, emitting sphere like a subtle cosmic bubble. These expanding shock fronts don't just light up the sky, they also serve as gigantic particle accelerators. As the shockwave plows through space, it can boost charged particles, protons and atomic nuclei, to nearly the speed of light. In other words, supernova remnants are factories for cosmic rays, the high-energy subatomic particles that rain down on Earth from all directions. For decades, scientists suspected that supernovae were the source of most galactic cosmic rays, but it was hard to prove. Recently, gamma-ray observatories have caught the telltale high-energy glow produced when these speedy particles smash into surrounding gas near supernova remnants. In remnants like IC443 and W44, we see the unmistakable signature of protons accelerated to relativistic speeds, emitting gamma rays. This was essentially conclusive evidence that supernova remnants, as Bard and Zwicky predicted long ago, give rise to cosmic rays. Thus, a supernova remnant not only glows brightly, it invisibly floods the galaxy with cosmic rays, seeding high-energy particles that will eventually reach Earth and pepper our atmosphere. The material blasted into space by a supernova, those expanding clouds of gas and dust laced with heavy elements, eventually mixes into the wider galaxy. Over time, that debris will become part of giant molecular clouds, the same kind of clouds that stars form from. In fact, the shockwave of a supernova can itself trigger new rounds of star formation. When the expanding shell of gas plows into a nearby cold cloud of gas, it can compress that cloud, causing parts of it to gravitationally collapse and form new stars. In this way, one star's violent death can spur the birth of many new stars, a cosmic cycle of renewal. Our own solar system may bear the fingerprints of such an event. There are telltale isotopes in ancient meteorites that suggest a supernova's shockwave might have triggered the collapse of the cloud that formed the Sun and simultaneously seeded the raw material of the early solar system with freshly made heavy elements. We truly might be, in part, the offspring of a long-ago supernova. Supernova explosions, then, are a kind of cosmic fertilizer. They take the elements fused in the heart of a star and scatter them far and wide, enriching the galactic gas with heavy elements that will become part of the next generations of stars and planets. Without supernovae, the universe would likely have remained a dull place of hydrogen and helium gas, with maybe some stars, but no planets, no complex chemistry, and certainly no life as we know it. It took generations of stars, living and dying, each supernova adding more heavy elements to the galactic mix, to eventually build a planet like Earth with its rich diversity of elements. The iron in our blood, the calcium in our teeth, the potassium in our bananas, all were forged in some ancient supernova and delivered to the primordial cloud that formed our solar system. As the late astronomer Carl Sagan memorably said, "We are made of star stuff." Supernovae are a key part of what he meant by that. What remains after a supernova can be just as intriguing as the explosion itself. In a core collapse supernova, when the fury of the explosion has abated, the core of the star has been transformed dramatically. Depending on the original star's mass, that collapsed core becomes either a neutron star or a black hole. We encountered neutron stars earlier, the city-sized, ultra-dense spheres of neutrons left behind when a star's core is compressed beyond white dwarf densities. A neutron star is an object of mind-boggling characteristics. It packs more mass than our Sun into a sphere only about 20 kilometers in diameter. It's essentially a giant atomic nucleus, or as some say, a star made of neutrons. The density is so extreme that a single teaspoon of neutron star material would weigh on the order of 1 billion or more tons. The gravity at its surface is so strong that if you dropped a rock from a height of 1 meter, it would smash into the surface in a microsecond, having accelerated to millions of kilometers per hour. Neutron stars also often spin rapidly, because the original star's rotation speeds up as it contracts. A newly formed neutron star can rotate dozens or even hundreds of times per second, and many neutron stars have intense magnetic fields, trillions of times the strength of Earth's field. These spinning, magnetized neutron stars can emit beams of radiation from their magnetic poles. If such a beam sweeps past Earth periodically, we see a pulsing signal and call the object a pulsar. The Crab Nebula's central star is exactly this, a pulsar, spinning about 30 times a second, shooting out twin beams of energy. That pulsar's wind of high-energy particles energizes the Crab Nebula, making it glow across the electromagnetic spectrum. It's incredible to think that this tiny stellar remnant, perhaps 20 kilometers across, is powering an entire nebula 10 light-years in diameter with its spin. If the star that exploded was even more massive, its core might be too heavy to stabilize even as a neutron star. In that case, the core collapse doesn't stop at the neutron star stage. It continues collapsing, effectively disappearing into a gravitational abyss, a black hole. The formation of a stellar mass black hole is the ultimate finale for a massive star. The core's gravity wins completely, crushing the matter into a singularity and creating an event horizon around it from which not even light can escape. If a black hole forms at the core during the supernova, what happens to the outer layers? Often, they are still blown off in an explosion. In some cases, though, it's hypothesized that a star might collapse directly into a black hole with almost no explosion, a failed supernova, which we'll discuss momentarily. But in general, astrophysicists believe many of the most massive stars do result in supernovae that leave black holes behind. We might not see a neutron star in those remnants, which is a clue. For example, no neutron star has been found in the remnant of Kepler's 1604 supernova, leading some to wonder if perhaps a black hole formed, though most evidence points to it being a type Ia in that case. On the other hand, some known black holes in our galaxy are believed to be remnants of supernovae from massive stars long ago. Meanwhile, the supernova remnant, the blasted out shells of gas, continue expanding and evolving. Over the years and decades immediately after the explosion, the debris is extremely hot and shines brightly in X-rays. Over centuries, as it sweeps up more interstellar gas and expands, it can form beautiful nebulous structures visible in optical light. The Veil Nebula in Cygnus, for instance, is the remnant of a supernova around 8,000 years ago. Through a telescope, it appears as wispy filaments against the sky, like delicate lace draped across the stars. Each filament is a section of the spherical shock front, seen edge-on, glowing as it plows into surrounding interstellar medium and causes it to radiate. Another example, Cassiopeia A, the 17th century supernova remnant, is a patchwork of knots and clumps of glowing gases about 10 light-years across, expanding at thousands of kilometers per second. In X-ray images, we see different elements highlighted in different colors, iron in one place, silicon and sulfur in another, evidence that the star's interior was not ejected evenly, but in a turbulent mix, like a cosmic explosion, frozen in time for us to study centuries later. As these remnants expand, they eventually slow down. After tens of thousands of years, the shockwave fades, and the once distinct remnant merges back into the general interstellar medium. But by then, the deed is done. The heavy elements are scattered far from their birthplace, mingled with the primordial hydrogen of the galaxy. Let's step back and consider the broader picture. Supernovae in the context of galaxies. Our Milky Way is a vast city of stars, and supernovae are like the city's fireworks and factories combined. They are relatively rare in any given galaxy, perhaps 1 or 2 per century in a galaxy like ours, but across the cosmos as a whole, they're going off constantly. To put the prevalence in perspective, the observable universe contains hundreds of billions of galaxies. By some estimates, roughly 30 to 40 supernovae explode somewhere in the observable universe every single second. Think about that. Every tick of a clock, dozens of stars in myriad galaxies are ending their lives in magnificent detonations. Most of them, of course, we do not see. We only notice a tiny fraction, the ones that occur not too far away, or in galaxies where we happen to be looking. But they are happening, enriching those galaxies just as past supernovae enriched ours. Supernovae also play a key role in the evolution of galaxies. They are a form of feedback. They inject energy and momentum back into the interstellar medium, which can trigger some processes and halt others. In galaxies undergoing a frenzy of starbirth, many massive stars explode in relatively short order. The combined effect of dozens or hundreds of supernovae can create a galactic superwind that blows gas out of the galaxy's disk. For example, the starburst galaxy M82 has huge Bi polar outflows of gas seen in X-rays and H-alpha emission, essentially a galactic wind driven by frequent supernovae and stellar winds. These outflows carry newly made heavy elements out into the galaxy's halo and even into intergalactic space, spreading the enrichment beyond the confines of the galaxy itself. Over the lifetime of a galaxy, supernovae gradually increase the metallicity of the gas. Young galaxies early in the universe had few heavy elements. After generations of stars and supernovae, modern galaxies like the Milky Way have gas enriched with a few % of heavy elements. This has profound consequences. It's this enriched gas that forms planets. Without countless supernovae enriching the Milky Way over billions of years, our solar nebula might not have had enough heavy elements to form Earth or life. Now, not all star deaths lead to a dazzling explosion. Sometimes, nature is furtive. Astronomers have found evidence that some massive stars don't produce a classic supernova at all when they die. They implode and form a black hole quietly, a so-called failed supernova. How do we know? A few years ago, an ambitious survey monitored a large number of relatively nearby galaxies, looking for stars that vanish. Indeed, at least one case turned up. A red supergiant star in galaxy NGC 6946 was observed to brighten a bit, as if beginning to explode in 2009, and then it faded away forever. No supernova burst occurred. When astronomers pointed Hubble and Spitzer telescopes at its location, they found no star, just maybe a faint infrared source from some leftover dust. It appears that star simply collapsed into a black hole with only a whimper of light. This object, humorously nicknamed N6946 BH1, is likely a direct collapse black hole formation. The term massive fail has been used. The star failed to go supernova, and it might not be alone. Analysis suggests that perhaps 30% of the most massive stars could end their lives this way. They give off a brief flash or a faint fizzle, then wink out. It's a chilling thought. A giant star could collapse into a black hole, and an outside observer might only see a brief, subluminous glow or nothing at all. The mighty engine of neutrinos and shock might sputter out in some cases. We think this happens when a star's core is so massive that even neutrino energy isn't enough to reverse the collapse. The core just keeps collapsing, sucking in the infalling material. The outer layers might fall in after it, or some fraction might get blown off in a last gasp that's far weaker than a typical supernova. The result? A star vanishes, and a new black hole quietly takes its place. Astronomers are actively searching for more examples of failed supernovae by scanning galaxies for stars that were there and then not. It's a needle in a haystack challenge, but the case of N6946 BH1 has shown it's possible. These silent deaths are a fascinating counterpart to the flamboyant supernovae. They remind us that not every stellar death is a firework. Some are a hushed curtain. Fall. Let us return to the spectacular ones, because they have proven immensely useful to us in another, quite unexpected way. Measuring the universe. Type Ia supernovae, the white dwarf explosions, have a special property. They reach almost the same peak luminosity every time because the physics of their explosion is thought to be pretty uniform. They can be calibrated as standard candles. This is incredibly useful in astronomy. If you know the true luminosity of an object, you can determine its distance by comparing how bright it looks to how bright it truly is, because light fades with the square of the distance. Type Ia supernovae, after some calibration, serve as cosmic yardsticks. They're so luminous that they can be seen in very distant galaxies, billions of light years away. In the 1990s, two international teams of astronomers, one led by Saul Perlmutter and another by Brian Schmidt and Adam Ries, set out to use Type Ia supernovae to measure the expansion rate of the universe. They observed dozens of Type Ia supernovae in distant galaxies. They figured they could measure how the expansion of the universe has changed over time by seeing how distant supernovae's brightness versus redshift compared to nearby ones. The expectation was they'd find the expansion slowing down. Instead, they found something astonishing. The distant supernovae were dimmer than expected. They appeared too faint, which implied they were farther away than the standard cosmological model predicted. The only reasonable explanation
was that the expansion of the universe has been speeding up. Those supernovae had gotten farther away from us than they would have in a decelerating universe. In 1998, the announcement came. The expansion of the universe is accelerating, driven by something we now call dark energy. It was a discovery that shocked the scientific world and earned the 2011 Nobel Prize in Physics for Perlmutter, Schmidt, and Ries. And it was based fundamentally on the observation of distant dying stars, type Ia supernovae, as beacons across space and time. Thus, supernovae became tools for cosmology. By treating type Ia supernovae as standard candles, astronomers have been able to map out the expansion history of the universe. We've learned that dark energy accounts for about 68% of the current energy content of the cosmos, causing space to expand faster and faster. Ongoing projects continue to use supernovae to refine our knowledge of dark energy's properties. It's amazing to think, a white dwarf's explosive death in a galaxy billions of light years away can encode information about the universe's fate. Today, we discover thousands of supernovae in other galaxies every year, thanks to automated sky surveys and dedicated telescopes scanning the heavens nightly. Supernovae have become so important that multiple surveys are essentially designed to catch these cosmic flashbulbs flickering on throughout the sky. Even as we observe these distant explosions, we keep a wary eye on our own cosmic neighborhood. What if a supernova happened next door? The vast majority of stars in our vicinity are not the kind to explode. But imagine, for instance, if Betelgeuse were to go supernova, would it pose a danger to Earth? Astronomers have calculated that a supernova would have to be uncomfortably close to cause us serious harm, and luckily no. Star that massive is that near. Betelgeuse, at over 600 light-years, is far enough that its explosion, though spectacular in our sky, would not fry our planet. But supernovae can still affect us indirectly from somewhat farther distances. Earth's geological and biological records may preserve faint whispers of past supernovae. For example, scientists found excess amounts of the isotope iron set in deep sea sediments, dated to around 2003 million years ago. Iron, 60, is radioactive, with a half-life of 2.6 million years, and it isn't produced on Earth naturally. The best explanation is that a supernova exploded within a few hundred light-years of Earth around that time, sprinkling the solar system with a dusting of iron. It likely wasn't close enough to cause a mass extinction, but it may have subtly affected Earth's atmosphere or climate. There's speculation that increased cosmic rays from such a supernova could have altered cloud formation or increased mutation rates by delivering extra radiation at Earth's surface. One research study even suggested that the muon radiation from a supernova, about 150 light-years away, would give every living organism the equivalent of a few CT scans of radiation per year for a few years. Not an immediate die-off, but enough to potentially raise cancer rates or induce genetic damage across many species. We suspect that over millions of years, Earth has been exposed to a few supernovae within a few hundred light-years. They might have left imprints. Some associate a minor extinction event 2.6 million years ago with a supernova-related cosmic ray influx, though it's not confirmed. It's a reminder that while supernovae create and enable life via elements, they can also, in proximity, pose hazards. Fortunately, such nearby blasts are rare, and none are expected in the near future. The closest star capable of going supernova in, say, the next million years is Betelgeuse, or perhaps the somewhat more distant star Eta Carinae. Betelgeuse's recent dramatic dimming in 2019-2020 sparked excited rumors that it might be about to explode. It turned out to be due to a giant cloud of dust that the star had belched out, temporarily blocking its light. Not the actual prelude to a supernova. Betelgeuse is likely not going up in our lifetimes, but we can't be absolutely sure. If Betelgeuse does explode, it will be an awe-inspiring spectacle. At 600+ light-years, it could become as bright as the quarter moon, casting gentle shadows at night. It would be visible in daylight as a pinpoint glow. It would be the brightest supernova witnessed in recorded history, and it would be perfectly harmless to us. Astronomers aren't just waiting passively for the next nearby supernova. We are actively preparing for it. We have networks like the Supernova Early Warning System tying together neutrino observatories worldwide. If a star's core collapses somewhere in our galaxy, a torrent of neutrinos will erupt from it and reach Earth hours before the first light from the explosion does. SNEWS is designed to detect that neutrino flood and automatically alert astronomers. Essentially, a heads up, a star is exploding message. Imagine a future night, perhaps not far off. Late one evening, deep underground in a neutrino detector facility, hundreds of light sensors suddenly register a ghostly burst of flashes as a wave of neutrinos passes through Earth. Computers instantly recognize the signature of a core, collapse supernova, and SNEWS sends out a global alert. Within seconds, telescopes, robotic and human, operated all start slewing to target the region of sky from which the neutrinos came. Observatories across the world are mobilized. An astronomer sitting at home gets a notification on her phone and rushes outside to look at the sky. And there it is, a new star, where yesterday there was none, shining in our galaxy. Perhaps it's near the center of the Milky Way, or maybe, thrillingly, it's in a clearer part of the sky and visible to the naked eye. Across the globe, people step out and stare upward, witnessing a once-in-a-lifetime sight. A brilliant new point of light, a supernova in our Milky Way. This scenario is entirely plausible, and with our early warning systems and modern instruments, we would capture the event in exquisite detail from the very start. It would be the first galactic supernova experience for humanity with technology in hand. We would scrutinize it in every wavelength. Radio telescopes catching the first whisper of the shock breakout. Optical telescopes recording the rise and fall of its light. X-ray and gamma-ray satellites detecting high-energy flashes, and neutrino and gravitational wave detectors feeling the ghostly vibrations of the core collapse. The amount of knowledge we'd gain is incalculable. It would be, scientifically, like observing the birth of a neutron star or black hole and the forging of elements in real time. And beyond the science, such an event would be deeply emotional for us as observers. For the first time in centuries, humanity would directly witness the death of a star in our home galaxy. It would be a stark reminder of our intimate connection to the cosmos. We would likely talk about it endlessly on news reports, social media, in schools and homes. Everyone, everywhere, looking up at this brilliant beacon in wonder. Ancient peoples might have feared or worshipped such a sight. We would investigate it with science, but also, no doubt, feel a primal awe. Now, let's not forget there are even more extreme explosions out there in the universe. Supernovae on steroids, so to speak. In the past 2 decades, astronomers have discovered a class of detonations called superluminous supernovae, which are 10 to 100 times more luminous than standard supernovae. These beasts defy some of the traditional limits of explosions. A superluminous supernova shines so brightly that ordinary supernova metrics struggle to explain it. For example, one of the brightest ever observed, SN 2006 Juai, in 2006 outshone its entire host galaxy and radiated perhaps 100 times the light of a normal supernova. It's believed to have come from an exceptionally massive star undergoing a very exotic explosion. Superluminous supernovae seem to come in a couple of varieties. Some show hydrogen in their spectra, others do not. They likely have different underlying causes. One leading idea is that some are pair instability supernovae, explosions of extremely massive stars where the star is totally obliterated. In a pair instability supernova, the core of an ultra-massive star becomes so hot that high-energy gamma photons start converting into electron-positron pairs via Einstein's EXMC2. This drains pressure from the core, causing the core to partially collapse. The collapse ignites a runaway fusion of oxygen and silicon in the core that releases an enormous amount of energy, enough to blow the star completely apart. The star is utterly destroyed. No neutron star or black hole remains. It's a one-time, fatal explosion. Pair, instability, supernovae, are thought to be incredibly luminous because they convert such a huge mass of the star into energy. SN 2007bi is a candidate for such an event. However, these require stars of masses that are rare in the current universe. They might have been more common in the early universe when stars could form more massive with lower metal content. Another possibility for superluminous supernovae is a sort of power-up mechanism after the initial explosion. One hypothesis: the newborn neutron star left by the explosion might be a highly magnetized, rapidly spinning object, a magnetar. If a magnetar is born, it can pump energy into the expanding supernova ejector. As the magnetar spins, it loses rotational energy, and that energy can heat the ejector from inside, making it glow far brighter for a longer time than a normal supernova would. Essentially, the central magnetar acts like an engine revving under the hood of the explosion, keeping the debris illuminated. Another scenario: some massive stars undergo violent eruptions shortly before the final explosion. If the star ejected a shell of gas years or decades before the final collapse, then when the supernova explodes, its ejector may collide with that earlier shell. The collision converts kinetic energy into light, producing an extra bright display. It's like a cosmic traffic accident. The supernova slams into its own preceding outburst. This is believed to be the case for some superluminous events that show signs of interaction with dense circumstellar material. The presence of hydrogen in some superluminous supernova spectra suggests a dense shell of hydrogen. Rich material was around the star, likely expelled not long before the explosion. And yet, as if superluminous supernovae weren't extreme enough, nature has an even more dramatic trick: gamma ray bursts. These are brief flashes of intense gamma rays observed from distant galaxies, and we now believe many GRBs are associated with the deaths of very massive stars, essentially supernovae with an added twist. In certain cases, the collapsing core doesn't just form a neutron star, it forms a black hole, and in falling material forms a hot, dense accretion disk around that black hole. This disk and black hole system can launch twin jets at nearly the speed of light out of the star's poles. If one of those jets happens to point toward Earth, we see a gamma ray burst. For a few seconds, it can outshine everything else in the gamma ray sky. A long-duration GRB is thought to be the signature of a collapsar supernova, essentially a massive star collapsing to a black hole and producing a supernova along with jets. The GRB announces the birth of the black hole, and minutes to days later, we detect a supernova afterglow from the same location once the more isotropic light from the exploding star's debris emerges. GRBs are the most luminous electromagnetic events known. Fortunately, they are exceedingly rare and extremely pointed. The jet covers only a tiny fraction of the sky, so the odds of Earth being in the bullseye are low. If a GRB went off in our galactic neighborhood and was aimed at us, it could be damaging. Some have speculated that a GRB could have caused the Ordovician mass extinction 450 million years ago, though evidence is inconclusive. In any case, GRBs are another facet of star death. Basically, a supernova where much of the energy goes into narrow jets. They're like a more violent cousin of supernovae. For our documentary's purposes, they are a reminder that even among stellar explosions, there is a hierarchy of power, and supernovae themselves can have these special, ultra-energetic cases. Astronomers often call the supernova associated with a GRB a hypernova. Returning to our galaxy and the relatively near future, suppose one day that neutrino alert comes and the next galactic supernova lights up our sky. What would follow is perhaps the greatest astronomical observing campaign in history. Every available telescope would lock onto the object. We would watch in real time as a star's brilliance climbs to a peak, then gradually decays. We'd detect the telling signatures of newly forged elements. We'd likely pinpoint a neutron star emerging. We might witness phenomena we've theorized about, but never seen, like gravitational waves from the asymmetry of the explosion or peculiar dust formation in the cooling ejector. It would be a scientific bonanza. And yet, beyond the science, we'd all be part of a momentous occasion in human history. The first time since the advent of modern science that humans can look up and see a supernova with the naked eye. As the supernova fades, we would know that the story isn't truly over. The materials flung out will merge with the galaxy's gas and, over millions of years, help form new stars. Perhaps, millions of years hence, some of those atoms will find themselves in the flesh of living beings on some planet yet to be born. Supernovae tie together the life cycles of stars, the content of galaxies, and the emergence of life itself. Now we arrive at a profoundly philosophical realization. We are connected to supernovae on the deepest level. The very matter that composes us was forged in these stellar explosions. Every person you have ever known, every animal, every plant, every building, every drop of ocean, much of their substance was forged in a star's nuclear furnace and released by a supernova. We are the universe's children, made of star stuff, baptized by fire. When we contemplate a supernova, we are in a sense seeing a part of our own origin. Think about the iron in your blood. Those iron atoms were once at the center of a massive star, part of its very being. In that star's final moments, those iron atoms, and countless others, were shotgunned across space. They traveled, perhaps for billions of years, eventually mixing into a cloud that formed new stars and planets. On one of those planets, Earth, some of that iron became part of a young planet's rocks, then part of the food chain, and now flows in your veins, enabling you to live and breathe. The calcium in your bones was likewise forged in some ancient stellar cataclysm. The gold in a wedding ring may have come from two neutron stars, merging in a far older event. We are, quite literally, made of remnants of long, dead stars. Supernovae are not abstract, distant things. They are woven into our being. Thus, the death of stars is intimately linked to the birth of life. It's a beautiful symmetry. The universe's most violent events sow the seeds of creation. The end of one star becomes the beginning of so many other things. We live in a universe that is explosively creative, quite literally. As our journey nears its end, let's revisit the imagery of a supernova one more time, but now with all the pieces in place. A massive star's life ends in a flash of unsurpassed glory. The brilliant light we see is the funeral pyre of that star's existence. Yet, in that destruction, the star performs a final act of generosity. It creates and disperses the chemical elements that will build future worlds. It's as if, in dying, the star exclaims, "Take this, universe, for I will not need it anymore." The remnants expand and cool, eventually blending into the galaxy. Perhaps tens of millions of years later, some portion of that enriched gas cloud collapses, forming new suns and planets. On one quiet blue world, the heavy elements from that ancient supernova become the DNA of new life forms. Those beings might one day look up and marvel at the stars, perhaps not knowing that a specific star's self, destruction, long ago paved the way for their own existence. In our own case, we have the good fortune of knowing. Through science, we have decoded this profound connection. Every supernova we observe in the sky is a preview of sorts of the cosmic processes that made our world possible. There's a poetic justice. Supernovae may kill their parent stars' planets, but they create countless new possibilities elsewhere. They are agents of renewal. It's also a humbling reminder of impermanence. Stars feel eternal to us, but they are not. They are born, live, and die on timescales long compared to human lives, but finite nonetheless. The universe is not a static stage. It's a dynamic, ever-changing tapestry. Supernovae are some of the brightest threads in that tapestry, momentarily lighting up the cosmos to remind every observing consciousness that nothing lasts forever. Yet from the ashes of the old, the new will always arise. As we conclude, picture the Milky Way in your mind, a colossal pinwheel of stars. Scattered throughout it are the ethereal blossoms of past supernovae, the glowing Veil Nebula, the Crab Nebula, Tycho's and Kepler's remnants, Cassiopeia, and many others too distant or too ancient to see. These are the galaxy's way of perpetually reinventing itself. Our galaxy, and indeed every galaxy, is like a garden where stars are the flowers. Most bloom steadily, some wither quietly, and a few end in explosive blooms that scatter seeds for the next generation. In the great cosmic dark, a supernova is a beacon of both destruction and creation. It is the universe's way of taking a star that has reached the end of its fuel and using that moment not as a quiet fading, but as a creative, transformative event. It's a final act that resonates across time and space. If consciousness exists elsewhere in the galaxy, perhaps they too have stories of new stars appearing in their night sky, and perhaps they too came to learn what those really are. The next time you step outside on a clear night, look up. Among the thousands of stars you can see, know that many are living out their long, stable lives. A few might be nearing their end. One night, perhaps in our lifetime, or perhaps in a distant future generation, one of those points of light will suddenly blaze unbearably bright. Generations of humans will have come and gone without seeing it, but eventually it will happen. When it does, we will have front row seats to the grandest show in nature. We will witness in real time the death of a star and the birth of a supernova. And when the night comes that a supernova graces our skies again, I suspect we will feel an ancient, almost ancestral thrill. For this drama has played out countless times in our galaxy's past, and it was essential to our very being. In a way, we will be watching a distant cousin give its life so that, somewhere, sometime, new life can begin. It is the cosmos' ultimate paradox and promise. From cosmic death comes cosmic rebirth.
We are all stardust, made possible by the violent deaths of stars. Supernovae are the universe's crucible of creation, the fiery loops in the great chain of stellar evolution. As this story of cosmic devastation and renewal comes to an end, take a moment to ponder the next breath you inhale. The oxygen in that breath was forged in a star's demise billions of years ago. The cycle continues. Out in the galaxy tonight, another star is living its final act, and somewhere else, a cloud is collapsing to form new suns. The cosmos is continuously writing a story of endings and beginnings, and supernovae are some of its most eloquent lines. In their light, we see not only the power of nature, but our own origins. It is a story that connects the smallest human heart to the most distant exploding star, a story of cosmic destruction, which is, at the same time, a story of cosmic creation, a story that teaches us that even in death, there is remarkable beauty and meaning. This is the legacy of the supernova, from the ashes of stars, the seeds of life, and new worlds. Every supernova is a reminder that we live in a universe where devastation and grace are two sides of the same coin, where the death of a star can be the birth of everything we hold dear. And as we, children of starfire, gaze up at the night sky, we do so with understanding, reverence, and gratitude. For those tiny points of light are not eternal. One night, one of them will blaze out, and the cycle will continue. The universe will celebrate a brilliant death, and in that very act, scatter gifts of creation for the ages to come.